Okay, good morning, everyone. My name is Shingo Asamoto from Saitama University. Now it's the time to start JSCE online joint seminar named Advanced Technology and Issue Related to the Thermal Effect of Concrete in Singapore and Japan. Now I'm in Japan owing to the kind hosting by Nanyang Technological University. And then I'm very happy to welcome you. So let's start the seminar. So at first, I would like to invite Dr. Oshima to give the opening remarks. Now he also in the Singapore. So Dr. Oshima, could you please give the opening remarks?
Okay, thank you for your kind invitation. Good morning. Good morning, everyone. I'm Oshima, the chairperson of the Subcommittee of International Affairs in the Concrete Committee, JSCE. It is my great pleasure to welcome you all to JSCE online joint seminar. On behalf of the seminar organizers, I'd like to thank you all for your participation online. This seminar is a kind of annual joint seminar organized by JSCE, and this year, Nanyang Technological University kindly accepted our offer to be a host of the seminar. Due to the continuing effect of COVID-19, the seminar is being held online, but the situation is getting better than last year, and some of JSC members, including me, are in Singapore. Once again, I'd like to thank Professor Tan from NTU and also Mr.Lu from ACI Singapore chapter. The theme of this year's seminar is the thermal effect of concrete. This important topic includes mass concrete in hot weather, and fire resistance of concrete as well. Due to global warming and heat island effect in urban areas, ambient temperature tends to increase more than before. Recently, even in Japan, we experienced more than 35 degrees Celsius in the summer. And the temperature of fresh concrete after delivering to the site becomes more than 35 degrees. In Japan, the specification stipulates the upper limitation of the temperature of the concrete, and there is a strong demand to revise the limitation, particularly from constructors and concrete producers. However, this problem couldn't be resolved simply by revising the specification. But this involves the essential issues of quality control under such a high temperature. When the temperature of the fresh concrete is high, that of hardened concrete may increase, and that brings degrees in long span strengths. Moreover, the differential temperature in the concrete section is also significant, and that may lead to the sufficient cracking. Regarding the fresh concrete, workability of concrete may decrease due to the high temperature, and that brings practical problems such as a cold joint or insufficient concrete filling. Therefore, this is still one of the challenging problems for concrete engineers and researchers too. Concrete structures, including high-rise buildings, bridges, dams, requires huge amount of concrete during construction. And how to decrease the temperature of the casted concrete is also a practical problem. In this seminar, Mr.Lu is going to talk about the mass concrete problem in Singapore. And Professor Hosoda is going to talk about the overview of the problem regarding hot weather concrete and mass concrete in Japan, including specifications. And Mr.ONO and Mr. Kikuchi and Dr. Sugamata will give us the important information about mass concrete and hot weather concrete in terms of material science. And not only such a temperature rise in construction, but also in operation during the fire is also a serious problem. When a fire occurs, the concrete strength may decrease, and the spalling may happen due to the expansion. Particularly under high stress, the concrete behavior becomes much more complicated. I believe that Professor Tan is giving us an important lecture about such a thermal effect of concrete in the case of fire. Today, you will hear from an exceptional lineup of speakers, researchers, and engineers who are the experts in this field. They have a lot of experience about the thermal effect of concrete in general. I really appreciate the speakers who expand their knowledge to the audience. I hope that this seminar will open up the opportunity to exchange our knowledge and also obtain a strong tie between two countries, Singapore and Japan. Thank you very much.
Thank you very much, Dr. Oshima. Let's move to the lecture today. By the way, if you have any problem listening and if you have any problem, please let us know. We are not sure whether our audio system is working well or not. So if you have any problems, so please let us know. Okay, so firstly, I would like to invite first speaker, Professor Tan Hai from the Nanyang Technological University. His background and CV is shown here. He got a PhD in the UK and now working in the Nanyang Technological University. Professor Tan, could you please give your presentation, lecture?
Right. It's okay. That's an All right. Can you hear me from the internet?
Yes, I can hear you.
Good morning. Thank you, Professor Samoto, for the kind introduction. And today I'm going to talk about the fire-resistant HPC and UHPC. And the emphasis is on the materials research, how the material research is then translated into actual structural columns under elevated temperature. I'd like to acknowledge the funding support from MND and JTC on this project. So just a very brief background on the project. This is a 7-year-long project with JTC championing, and it is on the construction of underground caverns in Singapore, the space of which is huge. So the intention is to possibly create another layer of industrial and storage systems underground. And in this context here, there are two aspects. One is the passive system and one is the active system. We are not going to touch on the active system today, which is obviously a very important part of the whole design, but rather we're going to look at the passive system, underground fire structures. And in this context too, we only have time to talk about the UHPC and HPC. There are other exciting topics, perhaps another opportunity we can talk about them. So quickly, we move on to the material properties, and we would like to explore what is the main cause of spalling, because we are going to use high strength concrete, and what are the mechanisms to prevent spalling. And in this context, we also develop a theoretical model to talk about the aspect ratio of these fibers and also the dosage and relation to the strength. So spalling is not a new topic. It is becoming more severe with very high strength concrete. Here in this context here, we are talking about UHPC and HPC. HPC are those concrete above 90 or 100 megapascal. And UHPC actually has a lot of military potentials, and they are used for resisting penetration and so on for hardened structures. And the flexural strength of these structures could be up to 30 megapascal. It also has high ductility because of the involvement of steel fibers, and it can resist cracking, and you can show some sort of a post-peak softening model. But at the same time, it has great risk of spalling, particularly violent breaking off of layers of concrete when exposed to fire conditions. So there are at least two kind of thoughts, two schools of thoughts. One is pore pressure induced spalling, and that is to say when the fire is on one side of the concrete, vapor pressure travels both way, in and out towards the temperature zone, and as well as inwards towards the cooler zone. And when this front of layer pressure migrates inwards into the concrete interior, there is a build-up of pore pressure. And because of this high pressure, there is a danger of this pressure causing breaking out of layers of concrete. And that is the concept of pore pressure induced spalling. Another school of thought focus on thermal stress, and meaning for thick sections, when there's a temperature difference between the outer and inner temperature, then this will build up a thermal gradient, and this thermal gradient will obviously cause as well tensile cracking. And the kind of water creation depends on the temperature of the heated concrete, whether it is 200 to 300 degrees Celsius, where thermal hydro movement water takes place, or thermomechanical, or even at much higher temperature. So the cause of spalling is the movement of water, and how this movement of water could cause pressure in the context of thin layers, but coupled with thick layers, then you have a combination of pore pressure and thermal stress induced spalling. So in the EC2, part 1-2, although they mentioned about using PP fibers for 2 kilograms per meter cube, they did not mention about the grade of concrete. There was no advice on what grade of concrete that this dosage is adequate. In fact, it is not adequate at all for higher grade of concrete. There's also no information on the aspect ratio of the fibers and about other factors. So in view of the shortcomings, that's the reason and the motivation for the research. So in terms of the mechanism, quite a few guys have come up with different mechanism. You can see all the different theories put on here. Unfortunately, not many of them have actually gone into a very systematic way of studying the mechanism. One mentioned about the melting fibers flowing into the surrounding channels. Another mentioned about the ITZ theory, about the interfacial transition zone, whereby they form the connectivity of pore pressure, and another one is PITS. Short of going into individual and to give a kind of remarks for individual theory, the more credible one was the PP fibers, melting of PP fibers causing spalling, that we found out to be not true. So we are going to talk about this in due course. The other one is about the PP fibers helping to improve the permeability of concrete by increasing percolation through the ITZ zone, the interfacial transition zone. Again, this was not confirmed experimentally. It was just a hypothesis. So based on this, we are embarking a relook onto the spalling mechanism, and we are questioning the melting point, and we even use fibers which are even lower than PP fibers. For example, the ultra high molecular weight polyethylene fibers, the melting point is 145 degrees Celsius. It is even lower than PP fibers, and we found out that UHM WPV, unlike most people would think, actually perform the worst in resisting spalling. So the way we designed this series of program is that we look at UHPC with cylinder strength of 150 megapascal, and we introduce PP fibers and steel, also PP fibers with aggregate, and the aggregate size range from 0.6 to 2.3 to even 5 millimeter. And we measure the residual permeability test using this torrent, and we put them all into the furnace subjected to ISO 8345 curve. So here we look at the combinations of PP fiber content and the steel fiber content. It is worth noting that without any steel fibers, the concrete cylinders could still perform well if the dosage is above 2 kilograms per meter cube, for example, 4 or even 6. Then if you look at the steel fibers, without the PP fibers at all, none of them withstand heating. In fact, all of them broke into bits and pieces. So it is impossible for UHPC to resist fire without introduction of PP fibers. And we look at some combinations of the steel and PP fiber, for example, 157 kilogram and 2 kilogram per meter cube. We find that some of these cylinders are intact, and in fact, there is also some sort of synergistic effect between the PP fibers and the steel content, and not only that, PP fibers and the aggregate size. In this context here, you'll find that even with certain size of aggregates, for example, 5 millimeter, there is an ability of these aggregates to cause thermal mismatch, and that they are still able to withstand this fire onslaught, even with a low content of 2 kilograms per meter cube. So we also do the mixture composition of UHPC are shown there, and we have tested using with fibers and without fibers, and we look at the top one. The top one is using the residual permeability, and whereas the bottom one, we look at a system to measure the temperature, so to measure the permeability of this disc up to 300 degrees Celsius. And the reason is that beyond 300 degrees Celsius, the kind of spalling that we are looking at is not as explosive as before. And we find out that there are certain interesting discovery. For example, without fibers, all of them break into bits and pieces. With PP fibers, certain diameter, certain length, certain percentage, they appear to be all right. But the question is why this is so. And we found out that there is increase of an increase of 2 orders in terms of permeability from 100 to 150 degrees Celsius. So this is a key thing. It is not the melting of fibers that occur beyond 200 or even greater, but the key thing is what is causing the concrete to be more fire resistant is between 100 and 150 degrees Celsius. And you find out that with the fibers, there is a 2 order of magnitude increase in permeability before even melting of fibers took place. And we conducted XRD and TGA on DSC. We found out that the increase in permeability was not caused by the phase change or the chemical change of concrete, but rather it is due to the coefficient of thermal expansion. So you find that the PP fibers and has a very, very rapid increase from 100 to 150 degrees Celsius compared to the aggregate and the cement paste. And this combination of the thermal mismatch create micro cracks. And micro cracks could be observed on the UHPC on the left-hand side, where you could see that micro cracks will start appearing even as low as 105 degrees Celsius between the PP fibers and the matrix in the radial direction. And the higher the temperature, then you find that, for example, at about 170 degrees Celsius, some of these PP fibers will start to melt. At 200, these PP fibers completely gone, and so on. But if you look at the UHPC without the fibers, even at 105 degrees or 150 degrees, the cracks are much smaller compared to the picture on the left-hand side. And the micro cracks are very important to allow this increase in 2 orders of magnitude in terms of the permeability. So you will see that the interest zone is between 100 and 150 degrees Celsius. And when we conducted X-ray CT scan, we compute the number density in the connectivity of microcracks, area fraction of microcracks from micrographs pitched together. And we able to find out that with different types of fibers, for example, UHMWPE, as shown on figure B, you'll find that UHMWPE has even lower temperature than the melting of the PP fibers, which is at 169. It is 143. But you could see on figure B here, the UHMWPE broke into bits and pieces. However, if you look at the LLDPE, the linear low density polyethylene with 123.15 degrees Celsius, it has both a low melting point as well as a wonderful expansion coefficient. It is intact. All right. So also the UHPA 66, UHPA 66, which has a higher melting point, but still it remains intact. So this proves the myth that melting point is the cause of defense for fire. Rather, it is the thermal expansion coefficient rather than the melting point, as shown by UHMWPE. So if you look at the dimensional changes, this is a much more important figure compared to the melting point. You'll find that LLDPE has a very wonderful increase. Also, the PP fibers, these two. However, if you look at the UHMWPE, which is red color here, this has much less coefficient of thermal expansion. It is more or less linear, and it is very slow. And this corresponds to the permeability increase of LLDPE and PP fibers. So this is to dispel the myth that melting point or the ITZ zone. It has nothing to do with ITZ zone, nothing to do with the melting point, but more importantly is the micro cracks. Now, having known the cause of this mechanism, our next part is to formulate a theory to account for this. So what we do is we look at the Kosny-Kalman equation, whereby we focus on the modeling of individual fibers with cracks. So individual fibers is assigned a micro crack as shown here, and the thickness and the length and the width is assumed to be the same as the fibers. And we use this on the basis that there is a homogeneous permeability, K, and we assume this kind of porous bed media. And here we also vary the different length of fibers from 6 mm to 18 mm for the different types of the PP fibers. the diameter as well. And you could find that there is, with increasing the diameter of fibers has little effect on the spalling resistance, because when you maintain 0.33% volume, the larger the diameter, the smaller the number of connectivity. However, when you look at smaller fibers with diameter of 28 microns and so on, this remain intact. So not only the number of fibers is important, but also more importantly is the length of fibers. And the length of fibers is to increase the permeation or connectivity. And as shown here, these are the first number is to relate the diameter of the fibers. The second number is the length of the fibers, and the third is the volume. And the volume is important, but also the length. So these are the spalling tests for different length and so on for the same fibers, PP fibers. And we take on the CT scan, and we have these images of all these fibers for different grades of samples. More importantly, we found out that for those red samples, the red ones represent isolated fibers. They serve as reservoir, but they're not connected. However, the green ones are fibers with interconnectivity, and you find that they are able to transmit, or through this interconnectivity, the pore pressure can be dissipated. And you can relate that to the permeability figure on the right-hand side. So you could see that when you have a certain diameter, certain length, certain volume percentage, then the permeability increase will be substantial. And we need to have 2 orders of magnitude increase beyond 10 to the power minus 16 to be able to dissipate the pressure. So we also conduct many sampling samples. We put it all into this figure here, and we derive an equation relating the threshold of the coefficient of expansion relating to the length to the diameter of the fibers. More importantly, we are saying that with a higher dosage, with higher connectivity of fibers, for example, greater length, the dosage can be reduced. But if you want to have a shorter fibers, then you probably need to increase the dosage. So there is an optimal percentage whereby it will not impede workability during the fresh state. So the magic number is somewhere around 0.6 times 10 to the minus 16 meters square. And the aspect ratio of fibers must be or should be between 300 to 600. So that this is the ideal range for the range of fibers. And of course, we could have also correlated that with different grades of concrete. And if we do that, then we are able to come out with the dosage of fibers for different grades of concrete, different length and diameter, and so on and so forth. Right. So having learned the importance of the PP fibers, we now focus on translating that into structure. So we look at the PP fibers, 2 kilogram per meter cube. We now understand, even with 2 kilogram per meter cube, with a certain aspect ratio, all right, the quantification is a certain aspect ratio, we could prevent spalling to take place. And the steel fiber is only 78 kilogram per meter cube, which is 1%. And we look at the crack mouth opening test for this. And we also look at the microstructure using the SEM to understand the presence of the micro cracks, as we see here. And then we perform the structural performance on the column test. So from the lab test of materials, now we move on to structural. And we have shown that those cylinder samples made of HPC and UHPC work well for the low temperature, for the high temperature. But now we want to see whether they can also work well for the structural level. So we conducted 3 series of tests. Series 1 is for column dimension, uni-axial loading. Series 2 is for biaxial loading, and Series 3 is for ultra high performance concrete with low eccentricity. The number of tests are shown there. And we conduct the test inside NTU with this electric heating furnace that is capable of simulating ISO 8345 fire if we start the heating temperature from about 50 degrees Celsius. The initial heat gain is too fast, so we have to start a little bit later with a higher temperature. With the Series 1, we only vary the eccentricity, and 2 sizes of cross sections were used. In Series 2, we vary both the EY and EZ, but based on the 200 square cross section. But we also vary the axial restraint ratio, that is the external stiffness. And then lastly, we look at combinations of plain UHPC without fibers, or 3 kilogram of PP fibers, and combination of steel and PP fibers, and to find out whether or not these UHPC columns could resist spalling. So this is the Series 1 for 270 mil and 200 mil. I am very pleased to say that none of them show severe spalling or sign of spalling. Most of them failed by crushing of concrete on the convex side, and you could see tensile cracking on this side, and it is very nicely spread throughout. So this gives us the assurance that our design for HPC is indeed working, and it is translatable to also at structural member level. There's no crushing for very small eccentricity from 0, 30 to 50 mil. There's no crushing. And for the larger cross section, there is some concrete crushing at a small eccentricity, but this concrete crushing is because of the bending effect. So these results are shown here, where we have the mid-height lateral deflection on top and the axial deformation at the bottom. The mid-height lateral deflection obviously shows the temperature at which the column behavior starts to run away. The axial deformation shows that initially, when the column is applied loading, it actually expands because of the thermal expansion of concrete. But as temperature increases, the elastic modulus of concrete weakens. It then starts to contract, and the axial deformation is shown there. In Series 2, when we have biaxially loaded column, the neutral axis is actually on the diagonal axis, and you could see the cracks are actually on 2 adjacent surfaces. And again, no explosion was heard. Obviously, we couldn't see it, but you could see that there was no sign of delamination of spalling cover. And this talking about grade of 90 megapascal concrete. So again, it is we are happy to say it has passed the test. But then when we look at the Series 3 with 140, we see that for plain concrete, there is violent spalling. You could see this is spalled terribly. And for PP 0, there's also some sort of cracking and corner spalling. Even with PPST to 50, there is a surface spalling and so on and so forth. So clearly, but with PP alone, it is not able to resist spalling. So you need to use a combination of PP and ST. Whether it's PP alone or no PP, you'll find that there is extensive spalling. Only at the case of 50 mil eccentricity, you can see some surface spalling, but this is fairly minimal. So again, we think we are able to create a relatively spalling free for UHPC 140 megapascal. Although we could say that there is some surface spalling because of the higher eccentricity. And based on that, my student, Dr. Tu, has come up with a very nice model based on mechanics and based on similar triangle. He came out with this derivation on the NM interaction diagram, which is for cross-section, but under the context of slenderness effect, the column capacity would then be reduced, and this is shown by the P subscript called A. CS represents cross-sectional area in the NM interaction diagram. A represents ambient, and this interaction diagram is verified at two limit states. One is when the column is very long, very slender, then it will fill in the form of Euler buckling load, which is shown here. The other one is when the column is very, very short, the slenderness effect can be neglected. So the P column at ambient then tends to the cross-sectional temperature, cross-sectional strength at ambient. So this verifies two extreme limits, and this is, and when you put the eccentricity E to be 0, this is then back to the Rankine equation, which was formulated in 1877 or thereabout. And what we then do is to incorporate the effect of temperature into the diagram, but also the effect of eccentricity in the X, in the Y and the Z axis, so that we can handle the same problem using the same equation for ambient and for elevated temperature for both biaxial eccentricity. And the student conducted the conduction and convection and radiation and total strain and mechanical strain, assuming total strain was observed from the beginning to the end. The transient strain and creep strain were formulated from using the CEB FIP model code. And based on this strain curvature relationship, Dr. Tu did a wonderful job in that it does not only show the strength, the capacity, but also he was able to relate from the strain to the bending and to the deflection as well. So he could predict the deflection of the column at mid-height based on this simplification as shown here. And he could incorporate different types of springs and the ends. And then he applied this to a set of deflection curves for the load and so on for different types of columns and so on. And the mean is shown there, 96%. And he did it for his own studies, for HPC as uniaxial, and also for HPC, UHPC as well. So the analytical model has shown that it works for a wide range of strength from 24 megapascal to 93.2 megapascal. Also under the fire conditions, the EOB ratio up to 0.5. This is eccentricity, which is very high. Slenderness ratio of very high value. And it has summarized into here the thermal properties, dimensions, and boundary conditions, and so on. And this is available onto the website. If you click on there, and you should be able to apply it as well. So in conclusions, that unlike the conventional wisdom that talk about weakness of the ITZ zone or the melting of fibers, these are all myths. We conclude that it is the thermal mismatch, the expansion strain that is crucial for spalling prevention. We develop a model that shows that there is a relationship between the critical fiber dosage as well as the fiber length. And it is important to have 0.6 times 10 to the minus 16 meters square at 150 degrees Celsius, beyond which spalling will not take place. Steel fiber alone cannot prevent spalling. We need a combination of steel and PP fibers for UHPC, all right? And for UHPC at the material level, we could show that conclusiveness do not spall, and even at the structural level, it works for HPC. But for UHPC column, it still shows spalling under larger eccentricity. So this is something to share with researchers who are working only at the materials level. There is different level of expectation and different level of rigor if one were to translate from material to structural level, and one cannot do without the structural test. Lastly, the analytical equation has been proposed that can predict the column behavior as well as the load deflection curve and the capacity at ambient and elevated temperature, incorporating both eccentricities about the X and the Y directions. I'd like to also thank you for the researchers for conducting the hard work. I'd like to thank Dr. Liet for his work on UHPC, Dr. Zhang Dong for many days of discussion on the role of fibers and the wonderful model that he put up, and also Dr. Tu for the load deflection curve. With that, I'd like to acknowledge the Ministry of National Development for the funding of these three these PhD students. Thank you very much.
Professor Tan, thank you very much. You are very interesting presentation from the material microcracking to the structural analysis. So probably some audience want to ask something, but actually we will have the Q&A session later. So, but if you have any question, you can post your question in the Q&A in the Zoom. Then also in the Q&A session, you can also directly ask them in oral. But anyway, if you have any question, you can post Q&A chatting. So thank you again to Professor Tan. And then I'd like to move the next presenter. Okay, next presenter is Mr.Lu. He is now the president of ACI Singapore chapter, and then he obtained the Master and Lecturer at Tongji University in China, and then probably he also provided us a very practical experience to us in the Singapore. It's very, very valuable for us. So, would you please your presentation?
I cannot share.
Okay.
You must exit.
Not accept. No, stop share. Right. No. No. No.
Okay. Thank you very much, Dr. Hosoda, for your nice introduction. Good morning, ladies and gentlemen. Can you hear me? So it's my pleasure today to join the JSCE online joint seminar. So this seminar actually, I would like to share Singapore experience on temperature control of mass concrete. So my name is Lu Jinping. I'm president of ACI Singapore chapter. I'm also a managing director of Hitchings International Private Limited. So okay, my president, I want to discuss first is what is mass concrete. Means mass concrete condition. Then we follow by what's the problem for mass concrete. So how to do some mass concrete in hot weather, especially in Singapore. You know, we are in the tropical country, so our weather is very hot. So I will discuss some shell cases of mass concrete in Singapore, and also one case in Malaysia. So last is a conclusion. Okay, let's move to mass concrete. What is mass concrete? So according to ACI 116R, the definition of mass concrete is any volume of concrete with dimensions large enough to require the measures to be taken to cope with generation of heat from hydration of the cement and the attendant volume change to minimize cracking. So all these cases we think is mass concrete. So the design of mass concrete structure is generally based on durability, economy, and the thermal actions. So actually with strength often being a secondary rather than a primary concern. So for mass concrete, the major concern actually is durability, economy, and the thermal action. So the one characteristic that distinguishes mass concrete from other concrete work is thermal behavior. So it means for mass concrete, major concern is thermal behavior. But unfortunately, there is no definition in current code for mass concrete in terms of the minimum dimension. But however, many project specification retains the guidance given in BS A110 Part 1 1985 version, where the minimum dimension of the concrete to be placed at a single time if greater than 600 mm, and especially where the cement content is more than 400 kg per cubic meter. Measures to reduce the temperature, such as using materials with a slower release of heat or hydration, should be considered. But in Singapore, we have old standards called SSCP 65 Part 1 1999 version, clause 6.2.4, concrete in tropical country. So they mentioned in January for an element with the least dimension over 500 mm, the situation should be evaluated. But even so, the SCP 65 actually already withdrawn, but in many project specifications, these requirements still follow. So what's the problem for mass concrete? So first is a significant heat is generated in the first few days after placement. Then expect to reach maximum temperature within 1 to 3 days after placement. So heat is trapped and cannot escape quickly, will cause the problem. One is significant temperature difference. Interior of concrete is much hotter than its surface, so it will cause thermal cracking. The second issue is concrete mix getting too hot, more than 80 degrees C, will cause delay engine guide formation in short-term DEF problem. So concrete will go spalling or damage. So what's a thermal cracking? So thermal cracking develops when the tensile stress exceeds the tensile strength of concrete. So the random crack in larger foundation will form. So a series of vertical cracks in walls and the uniform space cracks in beams, particularly to longest dimension. So mostly a durability issue, easy pathway for air and water. So you can see below some photo or figures can show the pattern of the cracks. So in some severe cases, it may affect the structure capacity. So you can see thermal cracking is a concern for mass concrete. So second issue is delay engine guide. We call delay engine guide formation. So studies has shown that the long-term durability of sturdy concrete can be compromised if the maximum temperature after placement exceeds the range of 68 to 74 degrees C. The primary damage mechanism actually is delay engine guide formation, DEF. So DEF can cause internal expansion and the cracks of concrete, which may not be evident for several years after placement. Means it's a long-term problem. So DEF normally will happen after 10 or even 20 years. So you can see it's a SEM photo for the DEF. And let's say we can enlarge, see the, sorry. For the DEF, you can actually is a needle type of crystal. So when gypsum, actually you can see that etching guide, if it's a primary etching guide, actually not harmful. When gypsum reacts with hydrous calcium aluminate in a true solution reaction and acts as a cell retarder in Portland cement mixture, so they will form primary etching guide. This is a reaction, means C3A react with gypsum and the water, so produce etching guide. So this etching guide actually you can see got 32 waters. That's why the volume will expand. So the formation of primary etching guide occurs in the plastic stage of cement mixture and does not produce any significant harmful stress. So it means primary etching guide actually is not harmful. You can see the same photo. So what we are very concerned is internal software attack, we call ISA. So primary etching guide from an early age is destroyed by high temperature. Normally it's more than 70 degrees C. Therefore, etching guide develops again at later age in concrete structure, exposed to water, to either intermittently or permanently, and the cause expansion or cracking. So this is an issue of DEF. So what things if there is ASR, means alkaline silica reaction, they has a very particular important effects in promoting expansion from DEF related to ISA. So in the presence of reactive aggregates, ASR related expansion will begin during the heat treatment and the cracks will immediately occur. So etching guide forms in these cracks or other pre-existing weakness and is considered responsible for the subsequent additional expansion and the cracking. So it means ASR is actually promotes the DEF. So you can see this ASR gel. So we promote the etching guide DEF. So the expansion of the concrete elements or component, the reformation of etching guide was favored by pre-existing crack. High sulfur content in the clinker phase, normally 2% as SO3, and the high sulfur content 4% as SO3 in Portland cement. So normally, the historic holistic approach according to this mechanism for the ISA-related DEF is based on the presence of three essential elements. One is a micro cracking. Second one is a late sulfur release. Third is exposure to water. So this is three elements very essential. Only all these three happen, then ISA will happen. So it means first is a micro cracking, then late sulfur release, and the presence of water. Okay. So we want to prevent DEF, we must eliminate any one of these elements. Actually, in BRE information paper IP 11/01, they mention few cases. First is no list of DEF. If there should be no list of DEF induced damage, if one or more of the following applies. First, the concrete is not exposed to external water or moisture at any stage. It means no water supply. So it means DEF cannot form because no water. Second, the peak temperature in the concrete is below 60 degrees C. Third, the SO3 content of the cement is less than 2.5%. So means any one, not necessarily all three, any one of these conditions happen, then there is no list of DEF. Second one is very low list of DEF. There will be a very low list of DEF induced expansion where the temperature of concrete remains below 70 degrees C, irrespective of the cement composition. If the temperature always below 70 degrees C, the list of DEF is very low. The third case is low list of DEF. There will be a low list of DEF-induced damage where the peak temperature remains below 80 degrees C, and where alkaline content means sodium oxide equivalent content in the cement is less than 0.85%. But fortunately, in Singapore, all cement require alkaline content is less than 0.6%. So it means we are safe in Singapore for all cement if the temperature is below 80 degrees C. So actually, it's a DEF damage is very low risk. But the use of low alkali sulfur resistant Portland cement, PFA means fly ash at the addition level of about 20%, or GGBS at the addition level about 40%, will prevent DEF-induced expansion in concrete subject to peak temperature of up to 100 degrees C. If we use PFA or GGBS, so we can release the temperature up to 100 degrees C. So you can see actually we are use GGBS for many projects. The percentage normally is more than 60, most of the cases 75%. So it means actually we can require the temperature up to 100 degrees C. But however, further work is required to confirm that expansion is prevented and not merely delayed, and that the use of these materials has consequently been characterized and providing a low risk of expansion. So means still likely can be 100 degrees C, but still need to do further confirmation. Okay, so some cases, I mean, maybe we cannot require 100 degrees C, can be, lower. So in some cases, the DEF list we are increasing. Temperature of about 85 degrees C may be sufficient to cause DEF-induced damage in concrete made using a wide range of cement. The risk of expansion occurring will increase if the peak temperature increases about 85 degrees C, and at the time increases for which the temperature exceeds 85 degrees C, and the specific surface area of cement increases, particularly about 350 meters square per kg. Where the temperature is 85 degrees C, the risk of expansion will increase with SO3, MgO, and the alkaline levels in the cement, as well as other parameters. And there will be a high risk of expansion where one or more of the following thresholds are exceeded: SO3 more than 3.6%, MgO more than 1.6%, alkaline content more than 0.85%. So if in this case, we really have to take a concern for DEF. So in the paper, it also mentions the list of expansion can be assessed using the empirical relationship. Means the following expression has been suggested as a mean of estimate DEF induction expansion as a function of cement composition following cooling at the 90 degrees C for 12 hours. This is you can estimate by a calculation how much is expansion due to DEF. So SSC actually is a specific surface area of cement. Okay. So how we can do mass concrete in hot weather? But the issue for concrete in Singapore, maximum peak temperature, we call DEF or ISA. Critical temperature differential will cause early thermal cracking and potential cool joint formation setting time, because temperature very high, so setting time will shorter. The potential plastic shrinkage cracking. These are 4 major issues for mass concrete in Singapore. So here in Singapore, we have some standards. SS 544 Part 1, 2014 version mentioned the temperature of fresh concrete should not exceed 38 degrees C. When we press concrete, the fresh concrete temperature cannot more than 38 degrees C. In clause A.2, where the heat of hydration or X-ray cooling is likely to taking the concrete temperature above 70 degrees C, the potential for delayed engine guide formation should be considered. The state of knowledge on delayed engine guide formation and advice on its avoidance is given in BI information paper IP 11/01. I already mentioned before. Also CP 65, that means that the concrete temperature at the point of delivery shall not in general exceed 37 degrees C or 60 or 6 degrees C above the prevailing shed temperature, whichever is lower. So LTA MDA specific also mentioned maximum temperature within the element shall not exceed 70 degrees C. In the event that the GGBS is being added as cement substance at no less than 60% by mass to reduce heat of hydration, the maximum temperature within the element not exceed 75 degrees C may be considered for acceptance by engineer. You can see just now, this BIE paper mentions 100 degrees C if GGBS is more than 40%. So LTA is more conservative. So we put 60% of GGBS temperature is 75 degrees C. So what we consume peak temperature. So maximum peak temperature actually equaling to place temperature plus temperature rise from hydration. So place temperature depending on the raw materials temperature, batching, and the transportation. So temperature rise actually depending on cement hydration, mainly type of cement, casting method, and insulation. So we can estimate temperature of fresh mixed concrete, means placing temperature. For example, without ice, we can use this formula to estimate the placing temperature, means the concrete after mixing, the temperature of concrete after mixing. With ice, you can follow this formula. So here is a simple, okay? So estimating temperature for freshly mixed concrete, actually the temperature of concrete can typically be reduced by 1 degree C if any of the following reductions are made in materials temperature. For example, any 7.9 degrees C reduction in cement temperature will reduce 1 degree C of concrete. So 3.3 degrees C reduction in water also can reduce 1 degree C of concrete. So 2.9 degree reduction in aggregate also can reduce 1 degree of concrete. So 4.5 degrees C reduction in the temperature of fine aggregate can reduce 1 degree C of concrete. So here is a simple example. You can see if only with water of 28 degrees C, actually the concrete temperature can be 32 degrees C. But if we use chill water 4 degrees C, we can produce concrete about 24.8 degrees C. So with ice and the wet sand, actually we are able to produce fresh concrete with temperature only 13.3 degrees C. So means still have many ways to reduce the place temperature. So again, the mixer, chutes, conveyor belts, hopper, pump lines, and other equipment for handling concrete should be shaded, paint white, or covered with wet burlap to reduce solar heat. This also can help reduce the place temperature. So forms, reinforced steel, and the subgrade should be forked or sprinkled with cool water just before concrete is placed. So restrict placement of concrete to early morning, evening, or nighttime hours, especially in arid climate, can also reduce the place temperature. Let's move to temperature rise. Temperature rise, as mentioned before, can be reduced by low heat of hydration cement or combination. So lower total cement content, we can add silica film. Actually, 1 kg cement, 1 kg silica can replace few kg of cement, but the heat release actually the same. 1 kg silica film and 1 kg of cement, the heat release is actually almost the same. So lowest possible water content in mixing by using high performance superplicizer. So smaller placement like a multiple lifts, sandwich casting, all these can also reduce the temperature rise. Okay, the last, we can use cooling piping system, but also you need to include the cost and a lot of troublesome, right? So different type of cement generate various amount of heat. Low heat generating concrete mixture are always a wise choice for mass concrete to minimize potential thermal problem. Low heat generating concrete mixes use the maximum allowable level of low heat porcelain such as Class F fly ash or GGBS as cement replacement. So and there's a minimum amount of total cementitious materials that achieve the project requirements. So Class F fly ash generate about half as much heat as a cement that is replaced and is often used as at a replacement rate of 15 to 25%. So GGBS is often used as a replacement level of 65 to 80% to reduce heat. So two examples, one is a fly ash cement, another one is GGBS. You can see if no fly ash, 100 kg cement can cause about 12 degrees C of temperature rise of concrete. But if you use 30% of fly ash, the temperature rise only less than 8 degrees C. Same for GGBS. For same one cement, about 12 degrees C temperature rise per 100 kg cement. But if 70% GGBS can reduce up to, below 6 degrees C per 100 kg. You see? So this one, some of the example actually is the temperature rise also depending on the dimension, right? 1 meter, 2 meter, 3 meter, 4 meter. If we have same one cement, almost 12 to 14 degrees C temperature rise. 30% fly ash only 6 to 12, and 70% is 4 to 11. Okay, so you can see the effectiveness of fly ash and the GGBS to reduce the temperature rise. Okay, let's move to some practice of mass concrete in Singapore. Actually, we have developed a diabatic temperature rise for estimate the maximum temperature rise of concrete. So this system actually we can test 3 types of concrete at the same time because we have 3 containers. So each container can put 1 concrete mix. So in the same time we can measure 3 mix. So we do some study on adiabatic temperature rise for same one and the different level of replacement GGBS. You can see this results. 0% almost temperature rise can up to 45 degrees C, but for 70% can only about 25 degrees C. Even so, the temperature increase rate also significantly reduced with GGBS. Okay, I have one case in Malaysia. Actually, it's Penang second bridge. So they engage us as a consultant. This is a Penang second bridge. This is a mixed concrete mix design used for this bridge pier. So they use PBFA, GGBS, and the silica film. So the PBAC they call botulinum polarized fuel ash cement 75%, GGBS you use 20%, then silica film 5%. So cement contains 430 kg per cubic meter. They use vaporizer, and the water simulation is about 0.35. So you can see the temperature monitoring results. Actually, the maximum temperature is about 75 degrees C. So actually, the developer consultant have concern, DEF. They're asking to do assessment for external software attack and also internal software attack. So external software attack, we do analysis, we find we need three conditions. First is a higher permeability of concrete. Second is software rich environment. Third is pressure of water, presence of water. So when we do the test, we check the initial surface absorption for the concrete only 0.01 ml per square meter per second. It's much lower than the specification of 0.1. So RCP test is only 712.8 coulomb. That means the permeability is very low. So the element is pylon are in the outermost zone, and the element below cross beam were coated by styling. Means there is something type of waterproofing. So since we assure there's a possibility of water into concrete is very low. So it means the concretion external software attack is quite low risk. So let's move to internal software attack, because the thermal decomposition and the reformation of etching guide can occur only in concrete elements steam cooled at high temperature 80 to 90 degrees C. So the expansion of the concrete elements accompanying the reformation of etching guide was favored by pre-existing core. Cracks high software content in the clinker phase as 2% of SO3 and the high software content 4% SO3 in Portland cement. So the peak temperature record for the first of the pylon is only 75 degrees C, below the thermal decomposition and the reformation of Shanghai temperature of 80 to 90 degrees C. So according to the cement test report, the software content expressed as SO3 is only 2.3 to 2.4%. It's less than 4%. So no micro cracking found in the petrography reports. We did a petrography test analysis for the concrete. So it means the internal software attack is quite low. Another case study is actually N Ting General Hospital, CD wall. So this CD wall, this temperature monitoring, the thermocouple location. So we check the temperature curve, and we found the maximum temperature is 75.4 degrees C. So actually maximum temperature difference is slightly above 27 degrees C as in the specification. So when we do the assessment, actually they satisfy low risk of DF, because the peak temperature recorded for this casting was only 75.4 degrees C, below the temperature requirement of 80 for low risk of DEF. And according to the cement test report, the alkaline content is only 0.32%, below 0.85% of the condition of low risk of DEF under BIE IP 11/01. So it means this case, we can consider low risk of DEF. Not only that, this still can actually meet no risk of DEF, because according to the cement test report, the sulfate content expressed as SO3 is only 1.98%, below the condition of no risk of DEF under BIE IP 11/01, 2.5%. So it means actually this case, even the peak temperature is 75.4 degrees C, there's no risk of DEF. Okay, now let's move to my conclusion. So mass concrete, minimum dimension of concrete as single cast more than 500 mm, and the cement content is more than 400 kg per cubic meter. So if peak temperature exceeds the range of 68 to 74 degrees C, the long-term durability of concrete can be compromised, especially due to DEF. So the limit of peak temperature can be relaxed from 70 degrees C to 75 degrees C for concrete with no less than 60% GGBS in Singapore. And the BI information paper IP 11/01 is used as guidelines in Singapore for assessment of DEF damage potential. So there are many measures for control of peak temperature, and the best choice is to use mineral admixture like fly ash and the GGBS. So thank you very much for your attention. Thank you.
Okay, thank you very much, Mr. Lu. It's a very informative information, practical way to considering the thermal effect. So some question is given, but later we can discuss again. So next, I would like to move the presentation from Japan. First presenter is Professor Hosoda. He the Professor Yokohama National University in Japan. He obtained all degrees from the University of Tokyo, and then his expertise the concrete engineering maintenance of concrete structure, and then he will introduce the JSCE assessment, thermal cracking. So Professor Hosoda, can you give your presentation?
Hi. Can you hear me? 聞こえますか？大丈夫？
はい、大丈夫です。
はい。
OK です。
はい、ちょっと待ってください。はい。Good morning, everybody, ladies and gentlemen. Dr. Asamoto, thank you for your introduction. It's a great honor for me to be here, to be invited as one of the keynote speakers. Today, I'd like to, I am Akira Hosoda, Yokohama National University, Japan. Today, I'd like to introduce some issues related to hot weather concrete and mass concrete, cracking, related to JSC, SSCS, standard specifications of concrete structures. Today, time is limited at only 30 minutes, so I cannot explain all the important issues related to SSCS. I will introduce several topics in which I have been deeply engaged. This is the SSCS design version published in 2017, which will be updated in next March. This one is materials and construction version of SSCS, which will be updated in September, 1 year later, 2023. Now I am the Secretary General of the revising committee of this construction version. And today, some of the topics are also related to JCI guidelines for control of cracking of mass concrete. This will be updated in 2024 or 2025. I am also one of the committee members of this revising. Furthermore, JSCE Concrete Committee now is editing the updated English version, including a design version, construction version, a maintenance version, etc. So after publishing, please purchase this English version. Right, today, I'd like to introduce 3 topics. First one is high performance air entraining agent to retain slump. Second one is control thermal cracking utilizing FEM based on JCI guideline or JSC specification. Final one, if I have time, I'd like to also introduce control thermal cracking based on past results. This is called Yamaguchi system in Japan. So first one is a special high performance AE agent. This graph shows the very much higher performance of AE agent compared to the normal one. This is one of the experimental results in hot temperature room environment. You can clearly see the high performance of AE agent, special AE agent, to retain the slump. As pointed out in the previous keynote lecture, initial defects can happen in hot weather concrete. It cannot be mitigated. And the time constraints, restriction for concrete placement in hot weather can be elongated. I'll explain in the next slide. But yes, we can avoid these cold joints or honeycombs. And there are several types of this special agent. This is the type to add from the hopper of the agitator truck. Now in the revising committee of JSCE, we are trying to install utilization of this high performance AE agent to retain slump. Actually, I am collaborating with many researchers and engineers. Maybe in the afternoon session, Dr. Sugamata will talk more about this high performance AE agent. This slide shows the policy of revision and now under discussion. So hopefully all these will be implemented in the next version of SSCS. Now in Japan, in the field of civil engineering, the upper limitation of concrete temperature can be set as 35. But according to this revision, concrete temperature, upper temperature can be increased up to 38 degrees. But concrete temperature should not be higher than 38 degrees. We can use 2 kinds of chemical agent. This revision can be applied both for plant adding type and also for site adding type. In parallel, now JSC committee is discussing the new testing method. The title of the testing method is test method of admixture related to slump retention and setting retardation of concrete in hot weather environment. Using this testing method, we need indices for evaluating the performance of fresh concrete. So now we're discussing that the slump loss should be equal to or smaller than 6 centimeters in 60 minutes in hot room. I mean 36 plus minus 2 degrees Celsius room. And for setting retarding performance, proctor penetration resistance should be equal to or smaller than 0.1 Newton to avoid cold joint in 3.5 hours in the same room. So fresh concrete with this special performance agent should be used for very high temperature environment. This is the policy of revision in 2023. Next, I'll introduce the control of thermal cracking utilizing FEM. Actually, two PhD students under my supervision tackled this target. Full-scale numerical simulation of girder bridges to mitigate cracking in RC-deck slabs. Actually, this is just one of the applications of the thermal stress simulation technique specified in JSCE guideline or in JSCE specification. If you're interested in this topic, you can refer this journal of ACT published by JCI. Do you remember the great earthquake in 2011, which happened in Tohoku region, severely damaged by tsunami? After that great earthquake, highway construction along the coastal line and also highways connecting the Tohoku highway and the coastal line have been rushly constructed. More than 300 bridges were constructed. They are completed already. And more than 100 NATM, NATOM tunnels were constructed in very limited time. If we investigate the existing structures, bridges, a very severe deterioration had been confirmed due to fatigue, de-icing agent, frost damage, ASR, anyway, combined defects. We wanted to mitigate, prevent this kind of deterioration in newly constructed bridges. We tried our best. So today I'll talk about the RC slabs, crack mitigation. So in order to mitigate those combined complicated deterioration, our countermeasures, our proposed countermeasures were low water to binder ratio, and to mitigate ASR or to give sufficient resistance against crowd attack, fly ash or BBGS had to be applied. Do you know expansive additive? Expansive additive was indispensable for crack mitigation, ETC. But unfortunately, still in some bridges, we found this kind of transfer crack in RC-deck slab. That's our target to prevent. Actually, one of the reasons of this transverse crack was thermal stress. This is not mass concrete, but the volume change of reinforced concrete, RC slab, is restrained by very stiff steel girder. That's one of the cause of this transverse cracking shown in this slide. In some lots, very severe cracking were confirmed. So to mitigate or to reduce thermal stress and also to know the influential factors, our team utilized thermal stress simulation. We call it three-level systematic simulation, consistent of three levels: material level, member level, structure level. We conducted verification in member level and structure level, utilizing temperature measurement, strain measurement, and also in some bridges, stress measurement. I was also surprised, but the JCI system, JSCE system can predict the temperature rise and temperature drop very accurately. But we need to give good simulation input. For example, CTE, coefficient of thermal expansion, we measure using a sample from the site. So in the specification, it's written that 12 of CTE, not 10, 12 of CTE should be used for GGBS concrete. But if we measure the real concrete, CTE was lower than the specified value. But anyway, temperature can be simulated very well. And we model the full structure, including steel girder and RC slab, and also our base isolation. Here, this is one of the important findings. According to the structural type, cracking index, lower cracking index shows the higher cracking risk. Shinkansen bridge was the 7-span continuous girder bridge. So continuous girder bridge shows larger cracking index. On the other hand, Hikohei bridge does a single-span bridge. So according to the structural type, the crack risk was totally different. But it was known generally, but quantitatively shown in this research. And for multiple span steel box girder bridge, CTE of concrete played a big role in stress. So if we something like that. Right. And also, as you know, in Jackie's book, initial concrete temperature affect a lot on tensile stress. So if we lower the initial concrete temperature, I know it's not that easy, but if we use low temperature concrete, thermal stress, tensile stress is reduced. Yes, so utilizing FEM techniques, some influential factors were quantitatively investigated, and they were utilized in cracking mitigation. My second PhD candidate for this topic continued investigation. Last month, he finished his PhD work, and he will work as a postdoc in my laboratory. He tried to show some practical curing method to mitigate thermal stress. For example, this one. If we use load heat transfer coefficient curing method, 4 means the transfer coefficient, heat transfer coefficient is small. Sorry. Oh, I was wrong. Higher value, 14 means the higher heat transfer. Heat transfer coefficient is high. Sorry. So if we use 14 value compared to the 4 value, for example, tensile stress is drastically mitigated. So his recommendation was to use a very simple curing method so that the heat transfer from the concrete to air becomes large. And also he proposed that the curing, effective curing only for 7 days. That's enough. Okay. So especially to reduce the maximum temperature from around 40 degrees to 30 something, that's quite effective to reduce tensile stress. So contractors may utilize this kind of knowledge or wisdom in mitigating cracking. As I mentioned in the this part of my presentation, thermal stress was just one of the factors, okay, but important factors. More important factor was the stress generated by stepwise construction. In the case of continuous girder bridge, the RC span length is quite large. In this example, RC slab placement was divided into 7 sections. He proposed, according to the stepwise construction, the tensile stress was generated in the existing RC slab due to the weight of new concrete. We also need to mitigate this stepwise construction stress. Dr. Nock proposed the effective strategy to mitigate this stress. And I will show you the journal paper related to this paper. Please look at the bottom figure, maximum residual stress after placing of slab. Red one was his proposal. The blue one was the real result in real bridge. So according to his proposal, maximum residual tensile stress can be mitigated, can be reduced so much compared to the real construction results. Okay. So this is one of our masterpieces in Tohoku highways. Finally, we could achieve crack-free 4-span continuous steel box cutter RC deck slab bridge, Fudaigawa Ohashi, in the north of Tohoku region. If you are interested in this mitigation of stepwise construction stress, it was published in Journal of Structural Engineering, JSCE. So please refer to this paper. Finally, I'd like to introduce another case for controlled thermal cracking based on past results. It's called Yamaguchi system. But actually, it's mentioned in JSCS briefly, but the details of the system or details of the methods are not described. So if you're interested, please feel free to contact me. Do you know Yamaguchi Prefecture is located in the west end of the main island of Japan? It's a local government, but this local government developed this unique system. Why was it necessary? Because one of the reasons is the thermal crack was very difficult to control. If you are an engineer or if you're a researcher, you can imagine how difficult it is to control the real thermal cracking in real structures. But in the system, a thermal crack has been well controlled. Official system was operated from 2017, already 15 years history. By this good management, win-win relationship between among many players, stakeholders have been achieved. I can say like that. Okay. The database and a kind of PDCA was achieved in real structures utilizing database. This slide shows the cracking condition, cracking situation of structures in Yamaguchi Prefecture at the beginning of the launching of the system. But in Japan, June, July, August are the hot season, as you know, so cracking ratio becomes high. But why in March, spring season, and December, very cold season in Japan, why cracking ratio is high? Can you imagine? In Japan, fiscal year starts from April. That's why Russian month, March, they're busy. So quality of concreting work becomes poor. Or we welcome Happy New Year in at the beginning of January. So again, December is Russian month. So workers want to go back to their hometown. That's why quality of concrete work becomes poor. Anyway, this slide shows the construction, concreting works is also very important. So in so-called Yamaguchi system, appropriate appropriate construction, as I mentioned in the previous slide, that's one of the keys. And a bit difficult to avoid summer season, but appropriate construction period, it was a second factor. And it's impossible to completely shut out cracking. That's why a crack control material like additional reinforcement or sometimes expansive additive, etc., should be appropriately utilized. So how can we achieve good construction? We can say easily in textbook or guideline, but our target is real structures, real construction. Okay, so this is very unique sheet. We call it revolutionary check sheet. It's nothing special. All those matters, 27 items are written in guidelines or specification, maybe in any country. Okay, preparation, transportation, placement, compaction, curing. All those are very basic matters in concrete work, but this sheet played a big role for achieving good concreting work. And this sheet was shared among contractors and supervisors of government engineers. What happened? According to this sheet, appropriate concreting work was achieved. Okay. For example, one of the fundamental matters for good concrete structures, as you know, a vibrator should be inserted into 10 centimeters in the lower layer. It's specified in the specification, but is it really achieved at the site? So this is one of the examples of good preparation. The workers or contractors provided color tapes so that they can control the height of the tip of the vibrator, okay, for example. Or these pink marks are expressing, showing the locations for the finishing vibrators, okay. So preparation is very important, okay. So, and government engineer, supervisor can easily understand that good concreting work is already prepared, okay. So good communication between contractors or workers and supervisors can be achieved. So this red mark is for controlling the height of the each layer, 50 centimeters it is. So good concreting work was one of the keys. So as you can see in this slide, harmful crack, ratio of harmful crack was drastically reduced in Yamaguchi system. But second point, good concreting work cannot mitigate, cannot shut out all the cracks. But if you are a real engineer, you know it, okay? So in Yamaguchi system, they accumulated the construction data, concrete construction data in their database. But the precondition is that the concreting construction should be appropriately done. Okay? That check sheet is one of the key methods. Okay? After some data is accumulated in the design stage, we can refer that database. Our next target, next structure, similar structure can be found in the database without any countermeasures like additional reinforcement. Crack width becomes very large. Okay? So in the design stage, they could judge that the additional reinforcing bar is needed. Okay? So they pay the money. Okay? That was not usual in Japan, but something like that. So they didn't use FEM, but this is another practical and rational but systematic method for mitigating thermal crack. So this is the sample of concrete construction data, the structural information, material information, and name of contractor, measurement result of concrete temperature, and furthermore, results of cracking, location, and the width. So they were the good references for the future construction. They are open, okay? From overseas, even from overseas, you can refer. And actually, I am utilizing this database for my research activities, like machine learning to predict maximum thermal crack. It's also published. Anyway, construction data is very valuable, especially database is so valuable from, I can say from experience. So this is very extreme case of the comparison of new structure and old structure. Of course, you can find no cracking in any structure, but the old structure constructed in 1970s showed very severe ASR reaction. So this is not the problem caused only by poor construction, but the material selection, durability designs. So by combining all efforts in design stage, construction stage, material selection stage, we can achieve a durable, beautiful structure. So this is an example of the figure to show the necessity of adding reinforcement. So in the lower range, maximum crack width becomes 0.3, 0.4 etc. So this is just one example, but based on these construction past results, they decide the appropriate reinforcement ratio. But utilizing type A, horizontal additional reinforcing bars, or type B, vertical reinforcing bars, they try to satisfy the required reinforcement. But this is the final information in my presentation. Yes. Crack mitigation example in the real construction, ABAT 2, ABAT 1. Actually, ABAT 1 was constructed later. So they tried their best to mitigate cracking in the ABAT 2 first construction, but unluckily, some cracks exceeded their threshold value 0.15 millimeter. Even though they tried their best. One of the reasons is that the length of the abutment was very large, 25 meters. So in the second construction, they applied expansive additive to the parapet. The cracks were completely shut out, 100% shut out. In the vertical wall part, they increased the reinforcement ratio. The cracks were more distributed. We can say one of the successful results of cracking mitigation in second abutment. This is all my presentation. I didn't prepare any concluding slide, but again, still technology is being developed, so we will try our best to feed them back to revising the SSCS JSCE, and also for future coming JCI guideline. This is the end of my presentation. Thank you for your kind attention.
Okay, Professor Hosoda, thank you very much for your presentation of introduction of JSC standard and also practical application of the standard and also experience in Yamaguchi Prefecture. Thank you very much. Okay, so now we will have about 20 minutes for discussion. Q&A. So we already have some question from attendee. So could you wait? I check firstly some.
I answer.
Okay.
Almost all questions already.
Okay. Yeah, you already answered by chat, so thank you. Okay,
Still one open question is.
Yes, open question.
Yeah, related to
Dr. Hosoda, one audience asked,
Okay.
So you mentioned it was already obvious that March and December, most concrete works are in hurry due to the perceived holiday. What is the mitigation and strategy Japanese government or researcher to improve the quality
Thank you.
such dashing months?
Actually, it's thank you for your question. That's not technology. That's the human management, or maybe. But anyway, to avoid such kind of not good, miserable situation, that check sheet, one page check sheet, was also provided. Okay, so. That's one of the answers, and second is the how can I say, contract of the construction, or setting appropriate duration, so that the rushing construction should be avoided. That's also necessary, and that's my opinion.
Okay, thank you very much. So, okay, so do you have any question? And then now one attendee raise hand. One Quen, do you want to talk? One Quen, you raise hand, so.
Sorry, my mute is.
Okay. So others.
I have a question, Ken.
Yeah.
I have a question for Dr. Tan. Can you hear me?
Yeah.
Okay. Relate to very interesting presentation. Relate to the high strength concrete fire resistance, especially ultra high strength. So I just want to understand for your 150 Pascal concrete, what is the mixed design?
Yeah. Okay.
Yeah. So the water binder ratio is very low. It's only 0.2. So we use a fair amount of silica film, and the cement content is extremely high. You fall off the chair if I tell you. Yeah. So it's more than 800. Okay, more than 800 kilograms. The reason for us to take that kind of research is that in hardened structures, these are the kind of strength that they use. So in fact, the hardened structures these days, they go up to even higher than that. So they go to maybe like, again, you may fall off the chair. It is conducted not in Singapore. It's 250 kilogram, 250 megapascal. Not the material level. It's in the structural level. So I'm sure in Japan, in your National Academy of Military, I think in Tokyo and all that, they have this kind of structures that to resist impact and all that. Yeah. So hardened structures, I think the use is mostly for hardened structures. I don't see how this could be used in Singapore because we have a building height limitation. So we cannot construct buildings too high, possibly around 80 stories because of flying. So, but military structures, I think that could be used. Yeah. But I think the more useful is the high performance concrete. Yeah. Not the UHPC for civilian. HPC is more useful than the UHPC. Yeah. At the aggregate size, you are right. We cannot use the 20 mil. Yeah. We cannot use 10 mil. Yeah, because this will create zones of weakness for the UHPC. So we can only use like less than 5 mil. Or 5 aggregates.
So means actually it's not concrete, still mortar.
Yeah. But we have to use a lot of steel because you can see that it is very, very brittle. The fracture surface is like glass. So if you don't use steel fibers, the whole structure is very, very brittle. But with the steel fibers, the whole structure is ductile. So there is a very nice post-tension, post-crack softening. Yeah, thank you for your very good question.
Okay, another question. Okay, you see in Eurocode, SSEN, actually I prepared a question here.
Yeah. Yeah, okay.
Okay, so EN 1992 part 1 -2 clause 6.2. They mention for spalling for high strength concrete, for concrete grade C55, 67 to C80, 95. So basically, if we have to prevent the spalling under fire, so silica content must less than 6% maximum weight. Right, but this case is no fiber lah.
So we have to use higher,
Very high,
yeah,
fiber,
but
right?
but we have to use the fiber. But the EC2 part 1-2, the way they treat the effects of the concrete material using the fibers is very, very it's not so adequate because they don't address the issue of permeability. So it depends on the permeability is the most important factor. So if you have very high permeability, then if you are able to create HPC with high permeability, which is obviously a thing very difficult to achieve, then it's possible. Otherwise, we find that the 2% like a magic number of PP fibers may not work. Yeah.
So since my next question also relate to the moisture, the permeability.
Yeah.
Actually, the fire resistance relate to the moisture content.
Correct.
Because the moisture in concrete under higher temperature, we need to find a way to escape.
Correct. Yeah.
So actually, the moisture content is very important for fire resistance.
Yeah.
So again, in this standards 5.5, relate to the concrete mentions the moisture content of concrete must less than 3%. Okay, so my next question relate to your testing. You see, your higher performance concrete, when you test for fire at what age? Because the moisture content depend on the age, right? You actually you cure for longer, few years, and even and compared to test at 28 days is totally different moisture content. So maybe the fire performance also different. So my question is, what's the age of your test?
This is a bullseye question. Okay, so if we test the HPC even with our mixed design, 1 month later, it will not work. So even though the water binder ratio is only 20%, but the impact of water inside the concrete is very, very damaging for this kind of high strength concrete, because the permeability is, as you can see, it is very, very high. Impermeability is very, very high. Permeability is very, very low, 2 orders low. So we actually tested more than half a year later. More than half a year later.
Yes.
I cannot tell you exactly the age, but it's more than half a year. Actually, it is close to like 9 months later. But this is not wrong in the sense that when a building fire is not so common, even though when we design for structures for fire, we design for. So it is assuming after 1 year later the fire will take place, not immediately after the thing. So this is the thing. Yeah.
Okay. Actually, I did a test for this moisture content.
Yeah.
For different strength class. I did a graph.
Okay.
This is the moisture content.
Yeah.
This is strength. So I find you see, because the standards mention 3% moisture content. So for high strength concrete, let's say you do not use fiber, the moisture content must be below 3%. But in the standards, they never measure how to measure the moisture content because moisture content depends on water simulation and also the cooling and the condition, right? So this standard looks very difficult to comply. You see 20%, how to make it?
So,
Okay,
so we actually measure the moisture content
Yeah.
by weighing the samples
Yes.
before and after.
Yeah.
We found out the moisture content is around the value they mentioned, but do not treat the, of course, this is saying from a researcher point of view, do not treat the EC2 Part 1-2 as the Bible, because they are formulated by human beings who are not expert. So if you follow the moisture content 3% and all that for that kind of high performance concrete without putting the fibers in, you'll be in for a rude surprise. You'll be in for a rude surprise.
Practical question, you see,
You
because
need to put in the PP fibers once you hit about, in fact, I would even say something like 70 megapascal and above. You have to put in the PP fibers for safety purpose. But for normal concrete, because the permeability is already low, there's no need.
Yes, exactly.
There's no need. But for high performance concrete, 70 and above, I mean, you ask me on the conservative side, professors are usually more on the conservative side, not like practitioners. I would say 70 and above, better put in the PP fibers, at least like 1% or something like that. But once you hit 90 and all that, you need to put PP fibers. But the fibers that you put in, it has got to be the one that with a high thermal expansion strength. Yeah, it's not the melting fibers. The melting point doesn't help. It's too late. Because 200 and 300 degrees Celsius, then they melt. The thing already spoiled. It's too late.
Because incur an inquiry from the Mancom. They have a project, use high strength concrete. So the consultant asking to prove the concrete mix design can make sure the moisture content is below 3%.
Even below 3%, it will still spoil. Without PP fibers, it will still spoil. If you are talking about 80, 90, is almost impossible. Because you don't need that kind of.
No, this is a plastic issue because in the Euro code they mentioned 3%. So the consultant very simple. I must comply.
You see some of the sample without the PP is poor.
I understand.
Even though they are 3% or thereabout, we actually measure the weight before and after. Even after 1 year, I mean, I let the cat out. It's quite long. It's quite long.
Okay. Thank you.
Okay.
So, from audience, some interesting questions are given to the probably related Mr. Lu and also Dr. Hosoda. This means so in the thermal cracking effect, I mean, we have the generally have the cracking, initial cracking, the early age. But how do you assess the long-term cracking propagation after thermal cracking? So this means he asked, what is the long-term effect of thermal crack? So how in practical, what do you think? For example, in Singapore, if you have thermal cracking, and soon after you detailing or injecting something to prevent crack, otherwise you just looking, then wait how propagate. So what is in practical the countermeasure for thermal cracking, especially in the viewpoint of the long term? Do you have any idea about that?
So you mean for the repair?
Repair, or what is the long-term effect of thermal cracking column? But probably durability issue, but also what is the extent of thermal crack?
Maybe I can. We were engaged by LTA to do a lot of these thermal effects on bridges, and they are to look at the thermal effect on bridges, and we also look at the repair system, not for the LTA one, but for HDB. The general takeaway is that when you repair, usually we would think that we will use a very high strength concrete material to repair on a weakened structure. But this, I have a very interesting discussion with Prof. Maikawa, and he mentioned that may not be a good thing to use very high strength for very, weakened structure. The strength should be kind of similar so that the stiffness is not a big change. Of course, it's non-showing and all that, but I think that's a very good point from Prof. Maikawa, not to use very, very high strength or compared to the weakened, because usually the weakened structure usually is like 30 MPa or even lower. And if you use very high strength, there could be some sort of difference in stiffness. And the issue of durability is a separate topic. We find that usually when you repair, then the cracks will appear somewhere else. And it's a how should I say, like you shift the water to another part and then they start cracking again and so on and so forth. So currently we are working with, it's a separate project with Dr. Kanda to find out how we can use the sacrificial anode and all that in a more effective way. Again, this is the work with Prof. Maikawa as well. This repair thing is a very, very complex one. It's much more complex than fire, in the sense that the part of the rebar that is corroded, the other parts that are not corroded, they actually attack the corroded rebar even much more. And we find that we are trying to use a kind of insulation around this thing to cut off. But insulation, and perhaps after the insulation with this another material, it may be better, but we are not yet in a concluding stage. We are still doing research on this. So there are 2 or 3 systems. One is the fine cracks, very, very fine. Hopefully it can be sucked in by the capillary action. The other 2 systems is by the Kanda system. Yeah. So we are hopefully in due time there may be some works that have been done on this. Sorry, this part here, we are still doing research, not concluded yet.
Do you continuously monitoring the cracking propagation in Singapore?
For the HDB project, we are doing that. Yeah, we are doing the site investigation of the flats, not for the LTA project. LTA project is for the thermal effect on bridges, and as everyone knows, there is an increase in the temperature worldwide. So the baseline for that increase is gone up. The T0, the ambient temperature has gone up, and we have to predict, like a magician, what happened 100 years later.
Okay, thank you. Dr. Hosoda, do you have also some opinion how we consider the long-term effect?
It's not so easy to answer that question, but I can say that environmental condition is one most important factors. Okay, even though we have 2 same kinds of cracks, if one is subject to very severe condition, we should take care. If very big crack is exposed to, for example, dry condition, no need to take care. So we have to consider. Okay, for example, his question is about mass concrete, right? So, for example, if we select abutment and pier, if we compare abutment and pier, we should take more care about abutment, because once the crack penetrates, water comes from the backside, backfill soil, for example. So that's why reinforcement can be corroded. But in the case of pier, what's the reason of the cracking? Internal restraint, crack doesn't penetrate. So in my opinion, no need to take care. That's the answer from me.
Okay, thank you very much. So some question given to the Dr. Hosoda, maybe you can answer later by text. So almost time is over. So I would like to have the break for lunch, and then we will restart about 15 minutes later, so Japan time 12:10, and then Singapore time 11:10. So, no, sorry. 12. More, sorry, I mistake. Yes,
12.
yeah, 1 p.m. in Japan and 12 in Singapore. So see you later. So could you join again in the starting time? Thank you. And also I would like to appreciate Dr. Professor Tan and also Mr. Lu and Professor Hosoda, your kind lecture and discussion. Thank you very much. So I would like to close the morning session. Thank you very much.
Bye-bye.
ありがとうございました。 Okay, so almost time. The afternoon session. Do you hear me? 小池先生、大丈夫ですか？
大丈夫です。
Okay, okay. Okay, so let's start the afternoon session, and then firstly, I would like to introduce the first speaker from actually he's Japanese, but from Singapore. So first presenter is Mr.ONO. He from the Taiheiyo, Singapore. And then he obtained the master and bachelor Saitama University, and then he now working the Taiheiyo Cement Corporation, and then he moved Singapore chapter now. So he will introduce Mr.Lu explain the DF and so on. So he will introduce this kind of information. So Mr.ONO, could you start your presentation?
Good afternoon, everyone. Thank you for your introduction. My name is Takayano from Taiheiyo, Singapore. Let me explain this title. これはアップしなくていいです。待ってますか？いや、待ってます。じゃあ、Okay. Let me explain about the separation effect of supplementary cementitious material SCMs on DF expansion. There are 6 chapters. First one, I'd like to explain about the introduction of DF phenomenon and general prevention. And second, not to generate DF expansion, reduce DF risk. And 3 is a study review. Just show you some liberal research. And number 4, show you our experimental study using local concrete material under the SSEN standard. And number 5, measures for DF in principal aspect. And finally, show you the conclusion. Firstly, introduction. DF ethylene is produced by hydration reaction with gypsum and aluminate at the early age, and ethylene also expansive needle crystal compound. But the DEF, delayed ethylene formation, is a phenomenon whereby ethylene is reformed through contact with water after the dissolution of ethylene due to temperature rise resulting from the hydration heat of cement. DEF occur when these three conditions are met. First one is excessive sulfate. Cement concrete material have sulfur trioxide and alkali content. And second one have a high temperature at the early age. Heat of hydration for mass concrete or steam curing for precast concrete. The third one is sufficient water supply at the ordinary temperature in a service period, wet or rainy environment. In this way, DF occur by complex factor, and expansion due to DF cause deterioration of concrete structure. This is an example of the deteriorated structure by DF. Okay, so next, it's a general prevention for DF expansion or DF cracking. One is a specified limit value, a maximum or peak temperature. And second one, maximum SO3 contents or alkali contents, mainly potassium ion or sodium ion and aluminate content. They are due to cement or binder material. And the other one is use supplementary cementitious materials such as fly ash or slag or silica fume. If you use fly ash or slag or silica fume, you may be able to control the above limit value. However, these SCMs is known to have further supplementation effect of DEF. From the above, the purpose of this presentation is to evaluate the effect of DF expansion suppression of SCMs in the Southeast Asia regions. The second purpose is to think of measure for DF risk in
practical aspect. Okay, this table shows the maximum temperature of limit value, maximum temperature limit in each country's guideline or reference or specification. And ACI and JCI and Singapore's Land Transport Authority's specification indicates temperature to 70 or less is basically. On the other hand, British or IFSTA's as shown as around as 60 or 65 degree is for no risk. No risk means even if sulfur trioxide or alkali is relatively high, DEF won't occur if the temperature is below 60 or 65 degree. In contrast, the peak temperature is relaxed to a maximum limit of 80 or 85 degree by using fly ash not less than 20% replacement or slag not less than 35 replacement, except LTA's specification. Singapore's LTA's stipulates that 75 is maximum temperature under 60% slag or more only. Okay, next, let me explain the previous research and study review as for DEF before our experimental outline. This is one research paper. This author used the fly ash, calculus type fly ash or siliceous type fly ash, and also use silica film. And this experiment shows a type 3 high R strength cement, so alkali is a bit high, and maximum temperature is 95, quite severe condition. And this result shows the siliceous type fly ash have more suppression effect of the expansion than calculus type 1. And for your information, Japanese fly ash is siliceous type only. And now Japanese fly ash is exported to Singapore nowadays. And silica film also shows suppression effect of the expansion. However, 8% replacement, silica film 8% replacement is not enough under 95 Celsius degree, but 80 Celsius degree, 8% is enough. This is the second previous research. This is novel research in 2021, and it's a long-term suppression effect. Author used white cement or early strength cement and W/6 for 50%, and maximum temperature is 90. It's assuming precast concrete. And this result shows fly ash 10% to 30% and slugs 40% to 60%. And this graph shows 300 days and 8 years and over 13 years. And result shows fly ash 20% or 30%, slag 40% or 6% replacement shows no abnormal expansion for more than 30 years. And expansion rate is still 0.1% at 30 years. So that's why the incorporation of fly ash and the slag at the appropriate replacement level. So in fly ash 20%, in slag 40%, greatly suppressed the expansion over the long time. So here is this thing, SCMs can be suppress the expansion even under high temperature and high SO3 and high alkali condition. Okay, and next page, let's show you our experimental plan assuming Singapore situation. This is used material. It's firstly ordinary Portland cement and fly ash and slag made in Japan, but their material are exported to Singapore. And fine aggregate, according to fine aggregate and coarse aggregate and chemical admixture, we collected their material actually used in Singapore. This table shows a mixing proportion. Target slump is 120 mm and water content below 2.0%. And we prepared the 3 types of blended cement. The one is fly ash 30% replacement. And second one is a slag 65% replacement. And third one is a ternary blended mixed fly ash and slag and OPC. And also for comparison, we made our ordinary Portland cement added potassium sulfate at the equivalent ratio to 2% sulfate trioxide. And W by B is 40%. And this experiment is carried out in Japan, but concrete mixing at 27 Celsius degree. This is in compliance with SSEN standard. Okay, this is our experiment plan. After we casting concrete, we make a cylindrical specimen. Diameter is 100 and height is 200 mm. And after that, we placed the specimen in a thermostatic chamber, a controlled temperature history. We using the 3D FEM analysis and just make a simulation curve. This is simulated inside mass concrete, and the maximum is 85 degree. And after that, we carry out the accelerated test. This is referred to Dagan test. Dagan test is an accelerated cyclic dry and wet condition. So 3 time cycle and 82 degree dry oven and 21 distilled waters submerge. And after that, so we measure the length and check the expansion ratio. Okay, this is the experimental result. It is average of 3 test pieces and expansion strain and age. Okay, first, so please take a look. Fly ash 30% and slag 65% and ternary blended. There shows that no abnormal expansion strain for more than 4 years. And expansive strain is only 0.01% to 0.03%. On the other hand, OPC plus sodium trioxide concrete have a much expansive strain, and which show that according to the electron microscopy, ettringite was observed in the interspace of the aggregate. So that's why SCMs are reducing DF potential even with high temperature at the early age. Okay. This next page shows the extra story. Experimental outline was same, but this study is verified the severe condition. Fly ash 30% and replacement and slag 65 replacement concrete containing potassium sulfate 2% or 4%, and also compared to the OPC plus 2% gypsum. In spite of sulfur trioxide is added for fly ash concrete or slag concrete, no abnormal expansion at the 2 years past. On the other hand, OPC plus potassium sulfate or 2% gypsum have a abnormal expansion. So that's the thing. DF expansion was suppressed due to the replacement with 30% fly ash or 65% slag, even with high temperature and alkali at the SO3 contents. The point is that fly ash is less replacement than slag. Okay. So what is happened in the microstructure level? So in order to verify, so we observed it by microscopy. This is a observation result, and according to microscopy, both potassium sulfate alkyl type and gypsum alkyl type have a lot of crack and a lot of interspace in aggregate by polarized microscopy. And also observed by electron microscopy, a lot of ethylene is generated in the interspace. This is that's why a microscopic observation revealed the occurrence of DEF. In contrast, we observed fly ash and slag concrete microstructure as well. So there was no characteristic finding of DEF in the microstructure. This means ethylene is not reformed, even if ethylene is distributed. Okay, finally, so I'll explain the measures for DEF practical aspects. So DEF risk is considered not only potential, but also likelihood. As I mentioned, DEF is complex phenomenon, so uncertainty is significant. In that case, engineer may be choose to use conservative estimate of the factor. So conservative estimate is based on the novel research. And there are three main factors of DEF, alkali and SO3, and the maximum temperature and the water supply. For practitioners, it is difficult to indicate conservative estimate and control their value correctly. Three main factors depend on the requirement specification, basically. Because if you use high strength concrete, binder contents become high, so alkali and SO3 contents naturally become increased. And if you use a mass concrete, so it depends on the thickness of concrete and difficult to control the maximum temperature. Water supply also same, as it depends on the condition of the environment. However, applying SCMs, we already experimentally confirmed that appropriate replacement SCMs can be suppressed even under severe condition. For example, high alkali and high sulfur trioxide or more than 85 degrees, sufficient water supply. Our experiment is quite severe condition, but no abnormal expansion. That's why the likelihood and the potential is we have to think about both situations. Okay, finally, show you the conclusion. First one, the suppression effect of SCM of DF expansion. In our unique DF accelerated test, and peak temperature is 85 degrees and dry wet cycling test. The blended ordinary Portland cement with 30% fly ash or 65 slag showed below. So first one, no abnormal expansive strain for more than 4 years. And also no abnormal expansive strain, even if potassium sulfate or gypsum is added. And third one, no characteristic finding of DF in the microstructure. And suppression mechanism is a various theory. But for example, the difference in pore structure, pore distribution, or calcium hydroxide content is very little in a blended cement. And the character of CSH hydrate may have effect DF suppression. And second conclusion, the measures for DF expansion in principal aspect. Number one, the peak temperature can be proposed maximum limit of 80 or 85 degrees by using SCMs with a proper replacement ratio in Singapore. And in DF, which has many uncertainties, using SCM is one of the most effective suppression measure for practical point of view. The advantage of the limit of 80 or 85 degree proposal. So one-time casting member height or one-time casting thickness can be increased without DF disorders. So we can expect to reduction in contraction period and larval saving and lower energy. Okay, thank you.
Yes, thank you, Mr. Ono. So, as in the morning session, we will have the question and the discussion time after the all presentation. So, I would like to move the next presenter. Next presenter is Mr. Kikuchi. He's now working in Shimizu Corporation, and then he obtained a master and bachelor degree at Tohoku University, and then his expertise the fiber reinforced concrete, massive concrete, high strength concrete in practical. So, Mr. Kikuchi, could you start your presentation?
Yeah. Good afternoon, everyone. Thank you for our introduction. Is my presentation sharing?
Yes, no problem.
Yes. I'm Kikuchi from Shimizu Corporation. I'm nervous because it has been 8 years since I have given a presentation in English. Today, under this title, I present, oh, sorry. Today under this title, I present case study of use of low heat type fly ash cement to prevent cracking in mass concrete. This photo shows 79 Robinson Road, which was completed in 2020. We used 8,000 cubic meters of this fly ash concrete for the raft in this building. Here is today's table of contents. I will explain 6 topics. First of all, as an introduction, an overview of crack in mass concrete. Photo shows a thermal crack that occurred during construction in Singapore. In Singapore, where the groundwater table is high, thermal cracks in underground structures such as raft and walls can cause leaks. Waterproofing materials such as Zypex are used to waterproof to the concrete structure, but if cracks appears in the concrete, waterproofing will have little or no effect. Why can't thermal crack be prevented? Mechanism here. Concrete heat up as a cement hydrate as a temperature and the concrete rise and fall, and the strain the concrete expand and contracts. The young modulus of concrete developed, and deformation contracted, resulting in thermal stresses. Furthermore, when the stress exceeds the tensile strength, the concrete cracks. In Singapore, slag cement with about 70% OPC replaced by GGBS is commonly used as a massive concrete. The figure on the right shows the result of homogeneous shrinkage measurement result. The homogeneous shrinkage strength of concrete with this slag cement is large and is a factor increase thermal stresses. To solve this problem, we turned our attention to fly ash. Fly ash cement newly developed by Taiheiyo Cement in 2014. And there are 2 types of fly ash cement called Taiheiyo Green Cement, which meet Singapore national standards and have received a green level certification. One of them is the low heat type fly ash cement with 21 to 35% OPC replaced by fly ash. It was marketed from massive concrete applications, but there was only one construction project at that time, and a small amount was applied in cement silos. Also, it was difficult to apply TGC low heat type, which had little experience. We explained the advantage of TGC low heat type and conducted the previous study, which was approved by our design consultant. Second topic is concrete requirements. Before describing the previous study, here are the application member and the concrete requirements for this project. The dimension of applied raft are 100 times 30 times 3 meter, and the concrete volume is 9,000 cubic meters. Next is the concrete requirements are as follows. Compressive strength is over 45 MPa. Target slump is 180 to 240 mm. Maximum temperature at the center of the raft is below 7 degrees C. The temperature differential between the center and surface of the raft is below 28 degrees C. Additionally, we were considering casting concrete in the 2 layers as a part of our construction proposal. Third topic is a previous study. In the previous study, we performed the 3-dimension concrete thermal stress analysis using software. Astiamax is commonly used in Japan to identify our raft's temperature and thermal crack risk. In our analysis, consider the difference between Japan and Singapore. In particular, for the concrete properties, we imported Singaporean materials to Japan and conducted concrete experiments in laboratory with controlled environmental temperature concrete experiments using TGC low heat type, slag cement, and OPC were led by Taiheiyo Cement. And based on the result obtained, Shimizu and Taiheiyo analyzed and double-checked these results. Here are the concrete properties using in the analysis. They are compressive strengths, tensile strengths, Young modulus, homogeneous shrinkage, coefficient of thermal expansion, adiabatic temperature rise, and creep. In the experiment, compressive strength, homogeneous shrinkage, adiabatic temperature rise, and the coefficient thermal expansion were obtained. The concrete properties were determined using general relationship equation in Japan. According to compressive strength result, long-term strength is comparable. TGC low heat type has the smallest homogeneous shrinkage, and slag cement has the smallest adiabatic temperature increase. Even the coefficient of thermal expansion differs between TGC low heat type and slag cement. Here's the result of the analysis. TGC low heat type and slag cement satisfies the maximum temperature of 7 degrees or less. In addition, all cement satisfies the temperature differential of 28 degrees or less. Slag cement is more effective than TGC low heat type in reducing heat generations. By the way, we focused on the thermal cracking index, which is a tensile strength divided by tensile stress. The higher thermal the higher the thermal crack index, the lower the risk of cracking. TGC low heat type with its low homogeneous shrinkage has a larger thermal cracking index than slag cement, indicating a lower risk of cracking. In the next phase in Singapore, we performed a trial mix concrete using TGC low heat type and fabricated the mockup under the direction of our design consultant. During the trial mix with the actual batching plant, we confirmed the slump test and the strength quality files were satisfactory. Here's the result of the mockup. The dimension of the mockup are 1.5 times 1.5 meters. Insulation was installed inside the mockup formwork and cured simulated actual construction. In addition, several thermocouples were installed on the mockup to measure maximum temperature and the temperature differential, and we have confirmed that TGC low heat type can achieve the maximum temperature of 70 degrees C, and temperature differentials are less than 28 degrees C, even in mockups. Fourth topic is concrete casting. Here is casting plan for raft. This is a mixed proportion of concrete strength class is C35 per 45. Water cement ratio is 39.5%. Casting plan here. Initially, the raft was to divide it into 6 blocks. However, in the order shortened the construction period, the casting plan was divided 4 blocks with a height of 1.5 meter per lift. Each concrete casting period at least 2 weeks was allowed the surface temperature of the raft to drop about ambient temperature. Next, the flow of concrete casting shown in the following photos. We took samples from all supplied ready-mixed concrete, performed a slump test, verified that it passed, and took specimens strength test. We continuously casting the concrete during the night. Once the concrete casting was completed, we cured the concrete with a plastic sheeting to reduce water evaporation and rain curing. Here is the condition and the concrete after curing. The concrete casting areas was extensive, and we don't believe we were able to survey all of the areas. And there were no serious thermal cracking on the surface or slides of the raft within the area surveyed. Of course, no water leaked occurred in ducts. In addition, compressive strength and temperature differential max temperature, which will be explained later after satisfy the quality requirements. Next to fifth topics is measurement and analysis for raft concrete. Here's the measurement plan and the third block of raft. Plan A is at the center and point B is at the surface. We set up some couples at each point in the height directions. And at only half of the height directions, we set up a strain meter, a non-stress meter, and a stress meter. Here's the temperature measurement of raft in the third block's result. Maximum temperature and temperature differential were satisfied concrete requirement. Here's a summary of verification analysis. We used the same model in the previous study, but used actual field data, such as ambient temperature, casting speed, casting temperature, and curing and concrete properties. For input the input values. Here's the analysis result. Calculated temperature almost agree where the measured value. In particular, temperature at the center, which is not easily affected by environmental condition, is simulated with good accuracy. On the other hand, calculated tensile stress is larger than measured value. Possible cause stress release due to small cracks cannot be observed visually, and creep property using analysis, precision of measured value by stress meter, and so on. Final topic is conclusion. 4 conclusions are presented. Concrete using TGC low heat type, which is fly ash cement, was applied to foundation raft of new building first time in Singapore. All requirements such as concrete strength, slump, and temperature, maximum temperature, and temperature differential were satisfied. No serious crack penetrating through the raft were visually observed. Crack control effect of TGC low heat type concrete could be almost verified by measurement result in the raft member and 3D FM analysis results. Here is important thing is Shimizu Corporation only used TGC low heat type first in Singapore. TGC is cement developed by Taiheo Cement and is fully available to all construction company in Singapore. So you can choose slag cement or fly ash cement low heat type. Special thanks Taiheo Cement, Taiheo Singapore, Island Concrete, and Home Rail Asia. Thank you for attention.
Okay, thank you very much, Mr. Kikuchi. Your nice presentation to practical application of Taiheo Cement, new developed cement. Thank you very much. Okay, let's move to the final presentation from the Japan. Final presenter is Dr. Sugamata. He is now head of Technical Development Center, MBCC Japan, for the release solution. He obtained the doctor degree in University of Tokyo, and then his expertise chemical admixture, SCC, SRA, and geopolymer. Dr. Sugamata, could you please start your presentation?
Thank you very much, Asamoto Sensei. So,
okay, it's shared well.
thank you. Okay, once again, my name is Takumi Sugamata from MBCC Japan. Firstly, it's my pleasure to have such opportunity today. So I'd like to talk about the latest chemical admixture technology of the company about having super slump retention and moderate setting retardation effect in hot weather concrete. Firstly, let me talk the ground about the environment surrounding concrete construction in Japan. So firstly, here is a record of RMC volume and number of RMC factories since 1990. So RMC volume was decreased almost in half from 1990 to the current status. And the number of RMC factories has also decreased from 5,000 to 3,000. So this makes the issue of the difference of RMC blank areas as well as longer off-site transport time. And here is a comparison of number of workers and worker age structures compared with between 1997 and 2010. The number of workers was decreased almost by 30%, and the number of young workers is declining. So this makes the issue of the shortage of skilled workers. And here is the daily average temperature in Tokyo since 1950. So in these almost 70 years, it has increased by 3 degrees Celsius. And here is the type of cement and binder used from 1990. OPC, ordinary Portland cement, stands for almost 70% of the type of cement. And recently, the SCM, like slag or fly ash, is gradually increased. And here is a type of sand used in nationwide Japan. So there are many kinds of sand used. However, the recently crushed sand and stone are increasing. And here is a survey result on RMC supply issue from both RMC suppliers side as well as construction side. So the most concerning issue was extra order from both sides. So this makes the issue of increasing waste concrete volume. So from a chemical admixture supplier's viewpoint, it seems that improving slump retention is one solution for all these problems. And here is another survey about important items when using chemical admixture and what requests expect to chemical admixtures for additional or enhanced functionality. This survey was conducted by owner, public officer, contractors, MC suppliers, or so on. So you can see that both surveys request more slump retention effect from this research. So from this background, our company decided to develop the new chemical admixture. Product's name is Mr.Lu. So Lu came from both biology as well as slump retention or super retention. And here is the image of the positioning for the chemical admixture having the relationship between the slump or dispersibility and the design strength. Here is a standard A water reducer, and here is a mid-range type of water reducer, and this product, Mr.Lu, is positioning between the mid-range and super plasticizer like this. So the advantage of this Mr.Lu is not only having a super slump retention effect, but also proper setting retardation effect and the superior rheological property is retained. So the concept of Mr.Lu is, first one, retaining concrete slump so long so that it enables long time and long distance transportation to meet the long delivery. And current technology needs to adjust a little bit higher initial slump, and the concrete is mixing. Before dispatching at the plant to meet the long delivery. However, this product, Mr.Lu, is easy to control the initial slump because of the long slump retention effect, so that RMC suppliers easily adjust the initial slump in the target slump range. And Mr.Lu has proper retardation effect as well. So especially in hot summer, the condition, more setting time retardation is expected. So using retarder is very common. However, depends on the raw material condition. It shows setting retardation phenomena. However, the Mr.Lu retain long slump with moderate retardation compared with standard mid-range water reducers. And here is an actual scale testing result in summer. So by using the Mr.Lu, the concrete and versus the normal mid-range water reducer concrete. The range of concrete temperature was 30 to 32 degrees Celsius. Then the both slump immediately after mixing are same. However, this mid-range water reducer concrete was dropped into 10 centimeter 120 minutes. However, the master ratio concrete retained the slump over 15 centimeter even at 210 minutes. So I'd like to show you some videos on slump and the B-funnel test. The normal mid-range water reducer concrete at 60 minutes, and the master ratio concrete was at 150 minutes. So both of them were similar workability. So here we go. So here is a mid-range water reducer concrete after 60 minutes later having 19.5 centimeter slump. And here is a master ratio concrete having the same slump at 150 minutes. However, not only the slump value, but also you looked at similar workability or rheological properties. Even the elapsed time was so different. And the next one is the B-funnel discharging time test. So in this case, you can see also the similar B-funnel discharging time of 4.8 versus 4.5 seconds. So the master ratio concrete can retain not only the slump value, but also the rheological properties for low. So next is why master ratio performs such a high spec. I'd like to talk about the super retention mechanism of this dynamic copolymer, which is used into master ratio. So PC have developed over the past 20 years and are now available in a very large variety of polymers all over the world. This is just one example of how polymers can be differentiated. So you can see several types of monomers make up one polymer. So the monomers, for example, the one is the cement affinity group, and another one is the retention function, which is capped with the affinity part initially. And also there are some type of the length of side chain from longer to shorter. So this retention effect, retention function, transforms to this cement affinity by alkaline hydrolysis in cement phases after time elapsed. Then you see this image of the chemical structure. The higher the affinity amount and the longer the side chain, the higher the initial dispersibility, like this dense blue one. However, it shows quite poor retention effect. Then if the more shorter side chain, and more retention function, like no affinity initially. The polymer performs very super retention like this with quite less initial dispersibility. So by combining these multiple polymers with different dispersing timings, it's possible to retain the concrete slump from immediately after mixing to a quite longer period, like 2 to 3 hours. And next story is the chance of the utilization for high temperature on this technology for high temperature condition in hot concrete. So here is the Japanese standard of placing concrete at hot weather concrete. For limit of transport time, AIS specifies using 1.5 hours from plant to construction site. And JSCE standard also specifies within 1.5 hours from plant to placing. And the environment temperature is over 25 degrees Celsius. And the limit of overlap time interval is also specified by Japanese JSCE standard within 2 hours. Then these clauses require concrete to have the overlap performance until up 3.5 hours to avoid cold joint. And another point is JSCE standard specifies the limit of concrete temperature by 35 degrees Celsius or lower. However, you see this figure, we've found this figure shows between the daily average temperature and concrete temperature at job site in Osaka's case. So we found if the daily temperature, average temperature is over 28 degrees Celsius, concrete temperature at job site tend to be over 35 degrees Celsius. And recently, there are many cases at job site, the concrete, when the concrete is arrived, the temperature is over 35 degrees Celsius. So in the standard, if the, in case of 35 degrees Celsius or higher, the countermeasure is mixing concrete with crushed ice or put outside of piping with water or something. However, it's not easy to apply those countermeasures inflexible at job site. So that applying master ratio in super slump retention effect and appropriate retardation effect for hot weather concrete is considered as one solution. So from the viewpoint, we have conducted several field trials and in summer, and here is one of the results. So the concrete temperature of master ratio conducted in the afternoon was over the limit by 35 degrees Celsius. And even under the very severe temperature condition, master ratio showed quite good slump retention effect, which keeps the target slump until range until 2 hours. And for another important part of the moderate setting retardation to avoid cold joint, Mr.Lu concrete got 0.1 Newton per square millimeter after 3.5 hours, which is an indicator of an acceptable range overlap by JSCE. So here is a summary of the presentation. So Mr.Lu has quite good super slump retention effect and moderate setting retardation. And the maximum summer temperature in Japan is expected to rise further in the future. This kind of technology is one of the effective measures in Japan. So that's all my presentation. Thank you very much.
Thank you very much, Dr. Sugamata. The very nice presentation of recent Japanese mineral admixture for retaining the slump. Thank you very much. So now all presentation is finished. So let's move to the question and discussion. So do you have any question or some comment? If you have, so you can post Q&A, or now not yet we received any question by chat. So if you want, you can raise your hand in the Zoom and then you can directly ask. You have any question?
Question, right?
Yeah, question.
I got a few questions.
Yeah, thank you.
Am I okay to answer?
Yeah, please.
Okay. I think the first big question is for Mr.ONO.
Yes.
I just want to find out your on your slide 7, you mentioned about 13 years. Is that measurement? How do you do the measurement? Because it's quite a long period of time, right?
Yes.
You actually measure continuously over 13 years.
This is previous research, not mine.
Oh, so continue.
No, I'm not sure. This is not my experiment.
Oh, not your experiment.
Yes, it's a
Okay.
research review, and this paper shows it's maybe periodically measured.
Okay,
And,
okay.
That means
You mean the 30.5 years one?
30.5 years.
Yeah, I know that Dr. Kawabata, he measured contact gauge. Contact gauge, and then expansion is rare. He said he measured contact gauge is not possible to do such big expansion. He measured directly using measure. Even the little bit inaccurate is okay.
Sure. 30 years. So this is from Japan?
It's from Japan.
Wow.
He continuously measure.
Wow, that's very impressive. Yeah. So the one question is about your fly ash and BS, right? Blast furnace slag. You use like 30 and 65. Yeah.
Yes.
I just want to find out, are there any kind of like a synergistic effect when you combine these two, the fly ash and blast furnace slag, in such a way that in a chemical way, how is that having a positive effect?
You mean that the ternary blended?
No, I mean when you have the FA and BS, is there any synergistic effect? Synergistic means like 1 + 1 more than 2. It's like very powerful, One by itself is 1, but
+1
more than
2.
Is there any synergistic effect when you combine these two? Like they help each other, or it's just it's just like 1 + 1 = 2.
Yes, as far as I know, so it's 1 + 1. So it's a slag concrete is high shrinkage gauge or a big original shrinkage gauge, and the fly ash is a small shrinkage gauge, and it's fly ash and slag combined. It's just like a middle.
It's kind of
Yes,
negating the effect.
Yes, just strength enhancement shrinkage gauge and fresh property is almost all characters become middle of fly ash and sand concrete.
I also noticed that in your slide you mentioned the JCI you only limit to 40% slag, right? In Singapore side we go up to 70%. Is there any concern on your side to use such a high percentage of slag? What are the concerns? Because I noticed that you only 40. Ours is minimum 70, sometimes maybe even higher. So are there any concern? Yeah.
Okay. I will answer. Actually, we have some slag cement. So we have three types of slag cement: type A, type B, type C. Type B is generally over 40 to 50, 60. So most popular one, the type B, and then we call the BB plus furnace slag type B cement. So that one is mostly used, especially footing or under column and massive structure. Generally, we always use BB now. So, but we also have the big demand to use over 60% replacement type C cement, but still under discussion because the reason is, strength development area.
It's very slow.
Yeah.
The major,
in the case of
only reason that you
are. Exactly. So in the case of Singapore, your ambient temperature very high. That's why strength development is a little bit accelerated. But in Japan, especially winter is our temperature less than 5 degrees Celsius, sometimes 0 degrees Celsius. So, it is very difficult to have that.
So the only concern is the early shrinking.
Yeah, I think so, because high replacement is good, because shrinkage is also reduced, and also other properties sometimes can be improved gradually. And also, but also big barrier is carbonation. Carbonation is a little bit weaker.
With a high slag cement.
Yeah, that is my understanding.
Okay. Sure. Yeah. I also see that you have a mock-up test in the Mr. Sorry. Yeah.
Mr.
Mr. Yeah. Yes. Shimizu.
さん聞こえますか？
はい。
Yeah.
Yeah.
Nice presentation. I see that you have some sort of mock-up test between your two horizontal layers. My question to you is, obviously the horizontal layering is very good, but what was the duration between the two casts, between the first layer and the second? Do you also factor it in your test bedding, in your mock-up test? Is it like 3 hours, 4 hours, or?
モックアップテストで、何段階かこうキャストするときにリフトありますよね。で、それで、その間をどういうふうにしてるかっていうので、そこでモックアップのときにその水平方向に特に問題なかった。水平は OK だけど、その垂直方向でこう重ね続けるときに問題はなかったかっていう質問ですけど。
日本語でよろしいですか？
はい。
モックアップは 1.5 メートル角でやってるので、実際の打設の1リフトに相当するので、重ねることは想定してやっていないです。
Mock-up test only the one layer. They don't check the.
Oh, they don't do the like
only one layer.
But what is your layer thickness like? Your cast
between the lift,
like layer by layer. How thick the layer is it like?
1.5 meter.
One shot.
1回で 1.5 メーターも一気にあるんですか？
It cannot be 1.5 meter one shot.
Yes.
Really? 1.5 meter one shot? Oh, okay.
How long? どれぐらいの時間でやります？
1.5 メーター。
layer by layer. 連続的に 1.5 メーターの高さでやるんですか？
そうですね。
何時間ぐらい？
何時間？24時間ぐらいですね。actual construction is 24 hours over.
For 1.5 meter.
For 24 hours. But it's layer by layer. Slowly, right? So each time is how thick?
1時間でどれぐらいの厚さで、どれぐらいの高さいくんですか？
なかなか計算してないんでわからないですね。I don't know.
So you have continuous
とにかく連続的にとりあえず 1.5 メーターはやられるということでよろしいですか？
いえ、その通りです。
Yes, exactly. It's a continuously. 1.5 hours.
Yeah, I'm interested in your FEM simulation. Do you use those hardened properties in your simulation of the convective heat transfer, like the expansion coefficient and all that? Is it using the hardened properties, or is it kind of the
strength development,
strength development, and also how you model this the heat of hydration coming out? Yeah.
これのシミュレーションっていう FM のやつは、基本的にアステアですかね。全部水場とか全部関係して考えて、共同発言とかも全部考えられてやってるんでしょうかっていう質問ですけど。
すべてアステアマックスです。
That is based on the JSCE massive concrete guideline.
Oh, that's a
guideline.
Okay.
Development and something.
Okay, thank you. And no more questions.
Okay, thank you very much.
Thank you.
Thank you.
So, other question from the attendees. So, do you have any question? So, if there are no question, I'd like to ask the Singapore's opinion. So now, Mr. Ono presents his proposal is 80 or 85 degrees Celsius for maximum temperature. But in my personal opinion, I think no need to have any limitation, because even if we boosting, accelerate at 90 degrees Celsius and so on, and then we continuously very small specimen submerging water expansion just 1,000 micro, 30.5 years. So now I'm wondering, why so conservative? Do you think it's very difficult to remove any maximum temperature limitation in Singapore? Do you think is it very difficult to remove?
It's going to be, I think, quite difficult.
But you have not experienced DF cracking in Singapore. Your experience. Do you have any examples like France?
There's a lot of cracking.
Is it DF?
Is this recorded?
No.
So what?
It is on YouTube. We're on YouTube. Yeah, please carefully.
Because now actually in Japan we have big discussion. So now we have mud cracking. And then when we found mud cracking, we always think, okay, this is ASR, alkaline silica reaction. But now another opinion, is it not possibility to have DF? Partial DF, that is a big discussion actually. So we are not quite sure it is a surely ASR or surely DF. Of course, even France, I think I'm not sure. So that's a big discussion, but so far we have not any crack the overstructure to have the maximum temperature over 85. So construction after 20 years, something like that after construction. But now practical engineers say, why we need to consider the DF? Because we have not yet experienced DF cracking. So Singapore, do you have this kind of discussion?
So far, frankly speaking, because DF is very long term, 10 years, 20 years. So far you can see, as mentioned by Prof. Tan, there are many cracking in the concrete structure. But unfortunately, nobody can identify since cracking is due to DF or due to other problems.
How about shrinkage? Dry shrinkage also can have such cracking.
Yeah, that's why it's quite difficult to identify which type of cracking.
It's
so
more like a belief.
So
if you do this, then you minimize the risk.
But you mentioned because Singapore actually, you see, all depending on our government authority. Actually, so far in Singapore, actually, most of the projects follow LTA and the W specification. That is 75 degrees C. Actually, already released already. Last time only 70. Now 75, we can allow for concrete with at least 60% of GGBS. Okay, already give 5 degrees more.
Okay.
But you see, for us, we have to be more conservative because once you release the temperature, then maybe out of control. Like for example, you see 100 degrees C. For example, actually, according to BI paper, you can up to 100 degrees C if you can control your raw materials. But the things who come to check, who can control all the other conditions. If the supplier or contractor have no control on the concreting mix design or other measures, so they may easily more than 100 degrees C and DF eventually come in. So quite difficult, practically quite difficult to control. That's why our LTA rather to be more conservative.
I see.
I'll discuss after the use.
So actually in Japan also we have many cracking them, but also it's very difficult to identify what is the main reason. So because also we discussing the blast furnace slab likely to have the cracking, but they say it is due to the low tensile creep and also low slow strength development, also high autogen shrinkage. But the difficulty is some slab has more shrinkage, more cracking. So one side is they say, okay, I had crack, but other side, no crack, complete slab is perfectly okay. Why you have crack? So very difficult discrepancy happened. That is probably same in Singapore. So that's why we need to study more probably.
Yeah, because you see the concrete structure is very complex structure. So you see, even we have crack, sometimes it's quite difficult to identify which kind of problem causes crack.
Because one factor which is very hard to measure is the restraint cracks. So this is something that is almost like it's very hard. With structures that are restraining, the cracks are much more than those like isolated hall where they are more free to move, right? So it is very hard to quantify the restraint stresses and shrinkage from restraint.
Okay. Yes. Thank you. So
but it's a good question.
Really, so
it's a very good question.
Good direction.
Good direction.
More effort.
That's why we motivate to work more.
Yes,
so
correct.
This kind of fundamental issue. Actually.
I think so. Especially I think this is in the thermal effects on bridges in Singapore. There will be a kind of upward revision in terms of delta T. For the value of delta T, please wait for LTA to release this information. There will be definitely a temperature increase, and this temperature increase obviously is not helpful to mass pouring concrete.
So temperature differential also very discussed with my Sri Lankan colleague. Why 20? Why 20? Not 25. Why 27? And then that is mainly based on the internal confinement. But in Japan, generally we always focus on external confinement from the foundation, the soil.
The soil. Okay.
So each very stiff soil restraint. External restraints are quite critical to cause the cracking, especially penetrate.
Correct.
That's why we always focus on this kind of issue using the three-dimensional big analysis by using FEM, JSCE guideline. So, but maybe also USA also they focus on the temperature differential, but we also discuss with the American engineer and professor. They said, okay, also external confinement is very important. It should be taken into account. So that's why only we say, okay, temperature differential is okay, but also
the restraint effect.
That is very important. So that is also very important.
Which is also related to expansion joints and
exactly.
The length and so on.
So that is classical and also very important issue. Okay, thank you. Okay, so any other question from audience?
I have one more question. It's about your rough foundation. Under what kind of conditions would you use the the kind of checkerboard pouring instead of the layering pouring. Because if you have a site really huge, like yours is the 30 meter by 100 meter, but what kind of conditions that you would consider using like individual checkerboard?
Checkerboard the piling?
Checkerboard, pouring, but it's checkerboard, and then but you have the mechanical joints. But of course, that will produce cold joint, right? They will produce cold joint. So you use that at all, or you always use layering?
You mean just surface coating for the?
Do you always use layering, horizontal layering? Because some sites are so big that and also you need a lot of people for layering, right? But under what condition you use this kind of individual pouring, and then you
individual pouring means
最後にくっつくところがあって、そういうところはどうしてるのって。
菊池さん。
はい。
なんていうのかな。その100メーター、30メーターってかなり大きい水平方法で、まあ、2つに分けてますよね。
はい。
で、そこをくっつけるところの、この間っていうのはなんか、どういうふうなこう処理っていうか、この2つ面の面をどうこうくっつけてるかっていう。
側面の話ですかね。
かな、多分。Pouring is
with mechanical joints. I mean,
mechanical
but it's
just two parts.
Yeah.
One
So
part
it's actually project management must manage very well. Otherwise, we cause cold joint. Because individual affect 6 power
this
and
one,
then
this
say you
one,
cut
and then you cut,
everything overall joint.
Yeah.
So it's a it's a problem. Later can become water and easily going. So normally we need to do casting continuously. Not individual.
Not individual.
You individual
Some
can
of the
cause
projects they
多分、この処理、
actually
1層目と2層目の処理ってどうされてるんですか？
This shrinkage, right?
Yeah,
Because the cold joint, yeah.
最初のリフトがあって、2つ目のリフトがあって、そこをどうするかっていうのと、まあ2面あるんで、なんかエクスパンディングジョイントみたいなのかなんかつけたりしてるんですか？
サイドはエクスパンションジョイントですけど、縦方向は何も処理はほとんどしてないですね。ある程度発ってっていうところ。
表面処理はされてるんですよね。
表面はしてますね。一番上ですよね。
それは、それはどういった処理ですか？普通に上削って水かけるってやつですか？
そうですね。はい。
Horizontal surface, they are crushed, and after that they pour the water and they cast.
Oh, they crush.
Crush, grinding.
Grinding.
Yeah.
If it is hardened already.
Yeah. And then the side, they have the expanding joint.
Expanding joint. Any formal joint.
Expansion
joint.
Expansion joint usually is about 200 meters, then you have expansion joint, right?
No.
Or are you talking about
10 meter? Expansion joint.
Oh, you're not talking about the structural expansion joint. You're talking about the joint with the wall.
The wall.
Okay. For the restraint joint, there's a restraint one. It's not the structural expansion.
10 meter. Because shrinkage.
That is
10 meters. Okay. So preferably it's a continuous cast, but sometimes area too big.
They
so normally, let's say one is too big. Normally it's a cast like it's a slope. Continuous slope. Both. So it's no joint.
Okay, thank you. Other question? Also, Dr. Sugamata explained our, how can I say it, transportation time. We say we need to cast from less than 1.5 hours
to 3.5 hours.
It's
the same kind of requirement for HDB.
Here, Singapore, actually, we have according to EN standards, EN 206, and also our Singapore standards for concreting is SS544. Our requirement 2 hours.
2 hours.
But the HDB that time require you how long?
No, here now all follow SS544 2 hours.
2 hours.
It is not dependent on the ambient temperature. I mean, if you cast night or if you cast the daytime, is it a different?
No, standards only 2 hours.
Only 2 hours.
Yeah.
Okay.
If you need longer, then you have to use retarding admixture.
It's similar to the Dr. Sugamata.
Normally it's 2 hours.
Okay, thank you. Okay, so any other questions? Sorry, my battery was finished. Other question? No. So, but almost time is coming the finish. So,
okay. Yeah.
so if there are any no question more, I would like to close the seminar. And then, okay, first of all, I very appreciate for the Singapore colleagues. Thank you for your hosting us and also organizing this wonderful seminar and very fruitful discussion with us. And also I appreciate for the Japanese lecturers to provide the Japanese state-of-art construction technology and DF issue and also JSC specification. So that I hope we have this kind of collaborative seminar frequently. And then also, if we have the collaborative research together, it could be very wonderful. So anyway, I would like to close this seminar. Thank you again. And then also thank you for your joining the Zoom members. And then also thank you for your many questions from the attendee. So, okay, so I would like to close the seminar.
I think there's no signal. It's not recorded.
Still recording.
Okay.
Yeah, it's
Yeah.
recording.
Sorry. Okay. So, okay. So, Koike sensei and Yamada sensei, shall we close this seminar?
Yes, we shall. Yes.
So ka. Oh, sorry. This is. Yamada sensei.
Hi.
Okay. So, shall we close?
Yes, we shall. No problem.
Okay.
Yes.
Okay.
Thank
you very much.
Thank you.
Again joining and then have a nice afternoon. Okay. Thank you very much. Thank you very much.
So actually, there are a lot of structures. I cannot get out because too many. And sometimes it
あ、どうもありがとうございました。小池先生も。
お疲れ様でした。
お疲れ様でした。じゃあ、特に、皆さんも退出しているようなので、これで終わって大丈夫ですかね。
これも YouTube も、これも、もう、ライブももう、これ止めりゃ勝手に止まるんですかね。
そうですかね。ちょっとこれ一応レコーディング停止しこれはどうやってライブ切るんだろう。いいのかな。
大丈夫っぽいですかね。
あ、小川さんか飯野さんも聞こえてますでしょうか。多分いらっしゃらないと思うので。
このことを。
はい。じゃあ、これ閉じちゃっていいですかね。
はい。
はい。
退出？山田先生のでこれ、ミーティングを終えられます？
どうなんだろう。退出しかできない。多分、ホストが土木学会のセミナーになってるんで。
じゃあ、このまま質で良さそうですね。
はい、して。Thank you very much for your attendance. Let us close this webinar. Thank you very much again. OK。じゃあ、退出しましょう。はい。